use pre-trained weights. In this example, TTS pipeline is composed of 3 different neural networks, which share some configuration parameters. Because it is tedious if all the users have to figure out the correct parameters and re-implement them in client code, we bundle them together. Now you can perform TTS with just a few lines of code. Let's look at the community growth. As of September 2021, there are more than 5,000 projects on github.com that use Torch Audio. If we look back, it was only 200 in July 2020. The adaptation of Torch Audio is growing. Thank you for using Torch Audio. Finally, let me share the current work the team is working on. Firstly, we are working to provide on-device ASR support. This includes model architecture with low memory footprint, such as Informer, which was developed at Facebook AI Research. We are also working to provide the beam search decoder that can work on mobile devices. We are also adding binary distribution of Torch Audio for mobiles. Lastly, we are working to promote the research and production use of self-supervised models. In this workstream, we added support for pre-trained model of Wave2Vec2 and Hubert in 0.10 release. We are working further to add components for downstream tasks, such as beam search decoder with language model support, datasets, and preprocessing used in popular downstream tasks. That's all I have today, and thank you for listening. Here are the resources for Torch Audio project. We are looking forward to your feedback. Again, thank you for using Torch Audio.
Hi, my name is Michael. I work on AI for veterinary health at Mars, and today I'm very excited to talk to you about our work in radiology and how we leverage PyTorch. So you might already know and enjoy some of Mars products, for example M&Ms or Snickers. But what you might not know is that Mars has 100,000 associates working in pet care, thinking about how to create a better world for pets every day. Mars also has a growing network of 2,500 veterinary clinics and hospitals in 20 countries. And Antech Diagnostics, a company that focuses on delivering high-quality diagnostics and imaging solutions to the whole veterinary industry. We found working in this environment, this tightly integrated ecosystem, very beneficial when it comes to building AI systems. It's easy for us to connect to doctors, to get their help, to start projects with them, and to learn from them. There's so much we can learn from them, and we're learning from them every day. Also, when it comes to deployment of our models, it's good that everyone working alongside the clinical value chain shares the same goals, shares the same principles. That's a situation that's very different from what you often hear from colleagues that work in human healthcare. Now, the pet population has grown enormously over the last years, and especially in the last 2 years. And while this is amazing for pets and pet parents, it also means that there's much more demand for high-quality healthcare for those pets. Now, on the other side, the supply side, that's extremely hard to match because it just takes time to educate a board-certified radiologist, for example. Now, that's one of the major facts why we find our work so rewarding and so interesting. Being able to build AI systems that support these amazing radiologists, these amazing veterinarians to be more efficient, to deliver more care to more pets, it's really what motivates us in the end. Now, in medical imaging, you often hear a paradigm that you only need a relatively small amount of data, has to be very high label quality, of course, but then you're basically good because those images are so much more standardized than natural images. Now, we found through experiments that this is not the case in our use case. We need a certain volume of data, otherwise we don't get the robustness that we need in production. And we have organized our data in different subsets based on label quality. The largest subset is the so-called NLP data, or NLP labeled data. Here we use an algorithm that we built based on work that has been done at Stanford, where we extract labels from radiology reports. And then we can use those labels together with the images to train our algorithms. Now, this process is inherently noisy, and we also have a data set, the so-called silver data, where each image is individually labeled by a radiologist. We have 250,000 images in this data set. That doesn't sound that much, especially if we work in natural images, but it already matches some of the larger academic data sets in radiology and human radiology in size, but has way better label quality. Then we also have a platinum data set, small test data set. It's every image is labeled by multiple radiologists, and we use this basically to assess the radiologist by radiologist variability and assess our models against that. We find using distillation really helps our training process. We use ideas from Noisy Student, combine those with earlier research on distillation. What we basically do is we take our best model, we predict all the images in our NLP labeled data set, and then we combine the NLP labels with our predicted labels. And we found that this leads to better results than only training on NLP labeled data or only training on distillation or noisy student style distillation. In inference, we found that using a fairly large ensemble really helps our robustness and also the accuracy for at least some of the findings. We have a couple of different feature extractors that are quite dissimilar from each other, and we use those to extract features. Then we combine those features with information about view, position, and body part that we obtain from earlier models, combine everything into 53 predictions. Now, 53 is not a number set in stone. It's always evolving, dependent on the feedback that we get from radiologists and veterinarians. We care a lot about data drift. We run our models now for months and months in shadow mode and have tested on tens of thousands of images while adding new regions, new hospitals to our pipeline. And we found basically no decline in predictive accuracy or other important metrics for us. We found this very interesting because that's very different than from what you often read in the literature. Now, we made a couple of different experiments. One of those is that we took an autoencoder, we trained it on a subset of our data, and then we predicted on an independent test set, and then looked at the reconstruction error. Now, we started, the first training subset was only coming from one hospital, from one organization. And then we added organization after organization and redid the whole process and looked at how the reconstruction error was evolving. And through this experiment and others, we have good evidence that you really need a certain diversity of organizations in your data to get to a place where you have robust enough models for production. Looking at the overall performance of our models, on this slide you can see the little symbols symbolize the predictions from radiologists for different findings, and then the curves symbolize the model predictions. And you can see that we already match radiologists for many important findings, and we see this all across different abnormalities we test on. The model I just talked about is only one of many in our production platform. Now we have models that predict body part, we have models that predict view position, we have models that predict the correct orientation of an image and reorients that to help the radiologist to be more efficient, for example. And we also use historical information from the patient in question and combine this with the predictions that our models produce to create a contextualized assessment per case and send that back to the veterinarians. When it comes to PyTorch, I like to say that we came for the dynamic graph, but we stayed for the ecosystem. We have been PyTorch early adopters. We really loved it in the beginning for rapid prototyping, but we definitely are amazed on how good it is now to bridge development and production. We built a complete training stack for this project with PyTorch and Hydra to make it very easy to configure. And we also, in production, we also really like to work with Torch script, because Torch script makes it very easy for us to hide some of the complexity of these large ensembles that we use. And also because it's very performant. Everything that drives performance there helps us a lot as well. And then just in general, the ecosystem. I mean, in this project we use Torch Vision, we use MMF, we use Detectron 2, we use Captain for model interpretability. It just amazed on how well the ecosystem has grown, and really want to thank you all, either working on PyTorch core and being so helpful when we have any questions, or all the ecosystem projects out there. Now, to give you an overview, at the moment we have 21 networks running on the whole X-ray or radiology platform. We do inference on around 15,000 images a day, and have already been done inference on 3.5 million images in total. The current system, and that's mainly coming from the reorientation of the images, already saves over 1,000 radiologist hours per year, which is amazing if you think back in the beginning on how scarce that resource is. I also want to point out that AI for veterinary health at Mars is way broader than what I just presented to you. Colleagues of us have developed and deployed a system that can predict chronic kidney disease in cats up to 2 years earlier than traditional diagnostic tools. We work in ECGs, other modalities in radiology, for example, dental or CTs or MRIs. And we recently deployed a system in pathology and also published about that experience. If you're interested to dive deeper into those topics, I listed some resources for you. If you otherwise just want to communicate about AI in veterinary health, please reach out on social. Very happy to have that conversation. And last but not least, thanks for listening, and thanks for all your great work on the PyTorch and PyTorch ecosystem.
Hi there, my name is Sabrina Smythe from Microsoft's AI Framework team. And I want you to imagine you're a performance engineer at a company, and your job is to help identify potential bottlenecks and potential scalability issues in your company's deep learning system that's already in place. Typically, this is how you'll start. You'll begin by running the deep learning model and capture traces along the way. But in order for you to optimize your model, you would need to gather profiling results and manually analyze them. But the problem is that traces can be gigabytes and gigabytes of data, and processing them manually can be a very time-consuming and annoying task. So once you've identified the changes you need to make to slightly optimize your model, you would need to run your model again, check the performance, and if the performance is great, then hooray, awesome, go get yourself a celebratory beer because you're done for the day. Otherwise, you'll need to go back to step one, recapture a profile, gather the results, find out the reason for the bottleneck, and fix it, try it over again. You might have to try this process an N number of times until the performance is satisfactory. You can imagine how incredibly exhausting that is. But here at Microsoft, we partnered with Facebook to bring performance engineers, data scientists, framework engineers, or anyone looking to optimize their PyTorch model, bring them a tool to allow you to collect performance metrics during training and inferencing and be provided actionable guidance on how to optimize your PyTorch model performance. And that tool is called Pytorch Profiler. In this session, I will go over the new Pytorch Profiler release and how you can get started leveraging this performance tool today. To end before a very short demo, I'll actually be speaking about our upcoming features that are really exciting, so stay tuned for that. Here are a few features we added in a version 1.9. We added distributed training view, memory view for tracking your memory usage. We added GPU utilization view for you to maximize your hardware. TensorBoard now has cloud storage support. And the last feature that we added that's super cool is that on Visual Studio Code, you can actually click on a trace file and it will take you directly into the source code where the bug is. That makes it easier for debugging. In version 1.10 of Pytorch Profiler, we released a few enhancements and a few new features. The first one being an enhanced memory view. This helps you understand your memory usage better. And we also added a few additional statistics like understanding your memory usage trend, which is quite useful. The second is an enhanced automated system. So we actually enhanced the feature that provides you performance recommendations to help you optimize your model. So whether you're lost on how to get started, optimizing your model, or need a few quick actionable hints on how to optimize it, that's the tool to use, which is really helpful. The third is around distributed training. Along with its ability to help you diagnose distributed training on individual nodes, Glue is officially now supported. The fourth feature is around correlating your operators in forward and backward paths. This helps you sort of map the operations that are found in the forward pass to the backward pass and vice versa. And these can all be visualized on a trace view. The fifth feature is around Tensor Core. We officially now support Tensor Core. Now, onto the demo. The first feature I'll be showing is Memoryview. Memoryview is a feature that allows you to understand the time and memory consumption that may have caused potential bottlenecks in your code, whether it is out of memory errors or memory fragmentation issues. This memory view allows you to see which operator exactly by the name, is contributing to the high consumption of time and memory. And in this release, you can now see the trend of your memory usage by showing you the memory events within the specified range that you've specified here. The next feature to show is distributed training view. So diagnosing distributed training view jobs can be very difficult without a distributed training view like this. And you can observe stragglers or workers not having enough work, etc. from these charts. And in addition, in this particular release, we support Glue. Now, the next feature I'll be showing is GPU utilization. Imagine you have a ResNet 50 model with a batch size of 4. And you can see that many of the workers are running, and you can see the device type, You can also see some of the GPU summary. So, the GPU utilization, SM efficiency, and some of the accuracy information, which are 3 very important metrics when it comes to GPU. But you can see that this is quite low. And if GPU utilization is low, this could potentially suggest that there is a bottleneck in your model. So there's clearly a bottleneck since your goal is to get 100% utilization. 100% utilization means that you're leaving no performance on the table and you're fully using your hardware to its full extent. Now down here, it suggests that perhaps increasing your batch size and adding tensor core will actually help you with this bottleneck. So the next run that we see here, you'll see that we have increased our batch size and added tensor core as per the recommended section at the bottom here. And you can now see that GPU utilization jumped a significant amount from the last run, just by taking these actionable steps. But there's still room to improve. So to further diagnose, we can actually move to the trace view. So this is where you get detailed information on some of the elements in the trace, the states that they're in, some of the events in 10 millisecond buckets, both on the GPU and CPU side, as you can see over here. Over here, we actually recorded a number of profiler steps that correspond to the training iteration in this particular case. And what you can do is you can actually add a record function to your program. And what that does is that it makes trace a lot easier to understand. So when we're looking at the trace, you can see that there's profiler steps. And if you zoom in, you can see that the operator's under the profiler steps, but it's actually hard to map it to your code. So this is exactly where the record function occurs. So the first thing that we typically do when we're on this trace is that we view the GPU utilization in the timeline. So in a trace view, you can easily observe specific areas of your program where the GPU utilization is low. And if it's high, awesome. That means that there's not much room to improve, that you're using your hardware to its full extent, you're not leaving any performance on the table. But if it's low, then that means that that's an opportunity to increase it. So that's what we're going to be doing here today. So we can actually observe unusual spikes or dips by zooming in and out. We can first observe this region over here that has an unusual dip. Here, it seems like there's 0 utilization, and then over here, it's 66.6 utilization. But what exactly is happening here? To get finer detail, we can actually go to the SM efficiency. So the SM efficiency, you can see that there's some sparsity micro gaps that are present here, and that could possibly be due to your PyTorch code looping over some vector or data structure, or you should be doing those things on a GPU instead. So over here, we added a function tracing. So you can actually zoom in and you can see that there's data loaders that are doing a bunch of iterations at the beginning of the epoch on the input data here. So that's what's causing the GPU to idle. In step 17, 18, 19, those all look good, right? It seems like GPU utilization and all those metrics are pretty decent. But in the cases where GPU utilization is high and SM efficiency is low, that could possibly mean that some of the SMs, some of their workload is actually pretty low. So they're not getting much work for them to be efficient and high. So what we can do next is go to stream 7. And stream 7 is where all the GPU activity happens. So you can see that it's very sparse in step 18, which is bad GPU utilization. So if you click on one of these, we can click on one of them in the stream and you can see, look, the data size that it's being worked on and some of the achieved occupancy is so low. And that's what's causing the low GPU utilization. But you're probably wondering, why does that happen? So there's a new feature that we released, and we can actually enable this async feature to map back to the CPU to see exactly what Python function are being used and what exact PyTorch operator are being used. So now you can use this Python function, a little sneak peek of a future release, and figure out exactly how to improve it, whether you can do it on a CPU or a fused kernel or some other technique that can help increase that utilization. So the last thing I'd like to show is that we can do forward and backward pass correlation by turning on this feature over here. So A lot of problems are happening on step 18, as you can see, and they're all in the forward pass. But if you were to correlate that, you can see that those are all replicated in the backward pass as well. So there's a lot of useful features in this demo that can really help optimize your PyTorch models. All right, so now this is the really exciting part. Here's a few sneak peek on some of the exciting upcoming features that we have planned. Okay, the first one is PyTorch function tracing. Okay, this is a feature that allows you to understand what's happening on the CPU side. Oftentimes, traces don't really give you a lot of information on why is the CPU idling. You know, it seems like nothing's going on. But as long as you're using Python, you'll be able to get all the function calls that you've used to be able to understand what is happening to your CPU being idle. The second feature that we're going to be releasing is a model attribution feature, okay? So traces give you very low-level PyTorch, operators. But why can't we at least see some of the module names associated with them? So with this tool, you will be able to allow yourself to map some of the time consumption into modules in Python, in a Python script. The last feature that I'd like to highlight is graph visualization. This is a super exciting feature that helps you visualize the Python model in a graph, which is really helpful for trying to debug and really optimize your models. Now, here's a few sneak peeks of a list of things that are coming down in our pipelines down the road. So, look out for these because these are really exciting and will really help make your workflow a lot more efficient. We put together a few references on tutorials and release blogs and a few talks that we've given, so please feel free to check it out and let's get profiling.
Hello everyone, my name is Michael Carilli, and in this talk I'll tell you about Cuda graph support in PyTorch, a new feature that improves performance by greatly reducing CPU overhead. First we'll cover the basic concepts, performance benefits, and limitations, then we'll go over examples of the new PyTorch API. A Cuda graph is a static record of GPU work, meaning kernels, kernel arguments, and kernel execution dependencies. The entire record of work can be replayed with a single Cuda API call. Graphs help because they greatly reduce CPU overhead for static workloads. During ordinary eager execution, each op incurs CPU overhead from Python, the PyTorch backend, and the Cuda driver. It's moderate, but it adds up. As GPU throughput increases relative to CPUs, we often see eager execution bound by CPU overhead. On the left is such a GPU timeline. The GPU runs each kernel faster than the CPU can feed it, and utilization is poor. But for network regions whose shapes and ops don't change across iterations, most of the CPU overhead is redundant. We don't need to rerun all the CPU work to compute shapes and launch individual kernels every time. We can record a Cuda graph of a single dummy iteration, then replay the graph in the training loop, which removes all that CPU work from the critical path. On the right, you see the GPU timeline for the same ops launched as a graph replay, and it's nicely packed. Here's a detailed example showing CPU and GPU timelines for a full CPU-limited eager iteration and an equivalent graphed iteration. Again, it's clear the graph replay has much less CPU overhead and a much denser GPU timeline. The pictures are not to scale. The graphed version ran 4x faster overall. Graphs also reduce jitter in distributed training. Jitter is a common cause of poor scaling efficiency because collective operations like all reduces need to wait for the slowest rank. CPU overhead is a common source of jitter. CPUs are more sensitive to sources of performance non-determinism like OS scheduling, lock contention, and competition with data loading and augmentation. The left picture shows two GPU timelines of different ranks for a CPU-bound network. The timelines are not well aligned. Rank 1 runs ahead. Its allReduce begins first and must spin waiting for rank 0's allReduce. By removing CPU overhead from the critical path, graphs reduce jitter. The right picture shows GPU timelines of two ranks using graph replay. You can see they're much better aligned. Here's a detailed example showing the end of a backward pass and an optimizer step. Each pair of timelines shows the GPU work on two different ranks in the same job. In the graphed case, not only are the timelines denser, but relative jitter is reduced. Again, these are not to scale. The graphed version was much faster overall. Here are some speedups we achieved with graphs for real networks. 1.1x on BERT at our max scale for the MLPerf 1.0 submission, 1.6x on MaskRCNN, again at our MLPerf max scale, 2.2x on DLRM as presented in our deep learning examples. 1.1 for BERT may not sound like much, but keep in mind the model was already highly tuned before adding graphs. Graphs do impose some restrictions. Like I said earlier, the graphed workload must be static. It also must be runnable without needing midstream CPU communication. In practice, this typically means no dynamic shapes or control flow, no sinks, and no essential CPU logic because the graph will ignore it. So how can you use graphs in PyTorch? There are three user-facing pieces: Cuda graph, a primitive graph wrapper; graph, a straightforward context manager that captures work in its context; and make graphed callables, a gadget that turns a callable, a module or function, into a graphed version. If your whole network is capturable, you should use the graph context manager to capture and replay an entire iteration. Here's how that works. First, run a few warm-up iterations to keep spurious, lazy initialization work out of the graph. Then, make some placeholder inputs to use for capture. Create a Cuda graph to hold the graph, then run a dummy iteration under the context to capture the work. Replays typically act on the same memory every time, so the graph will read its input data from the placeholder inputs used in capture. To compute on new data each iteration, first copy that data into the placeholders. And then replay, which runs the whole iteration's GPU work in one call. Params are updated and the latest loss value is written to the placeholder output, capture_loss. Here's a script where a whole network capture is impossible due to a CPU sink and dynamic control flow. In this case, we can use make graphed callables to capture just the capture-safe parts. Begin by creating dummy inputs for each callable you want to capture. Then apply make graphed callables to each part you want to capture. Unlike the graph context manager, make graphed callables does not need manual workload warm-up. Now just run the network as usual with the graphed callables dropped in. Each callable's forward pass runs as a graph. Note that unlike the graph context, you don't need to manually copy new data to placeholder inputs. Graphed callables backward passes will also run as graphs. Make graphed callables has some convenience features, but its replays run less efficiently than full network replays. Best practice is to use the graph context manager for full iteration capture when you can, and make graphed callables when you must. The Graphs API works with native AMP and native DDP. See the documentation for minor gotchas. Graphs should also be composable with JIT. You should be able to JIT a model, warm it up, and then graph it, although only with the NVFuser backend, and generally I'd regard JIT interoperation as experimental. If you've heard enough to consider Cuda graphs, the documentation is much better than this talk's brief summary, so take a look and feel free to file an issue if anything is unclear. Thank you for listening and enjoy the rest of the conference.
Hi, I'm Victor, and I'm here to talk today about performance in PyTorch. In particular, we'll be talking about how to make performance faster for everyone using PyTorch. Today, we're going to talk about four things. We're going to talk about performance, what it is, what it means, and why it's important. We're going to talk about challenges in improving performance. And we're going to talk about one of our main tools that is new for improving performance for everyone, which is called Torchbench. And we're also going to be talking about how this fits into a larger ecosystem of user-driven benchmarking. Basically, we're looking at performance. Performance isn't about one model, it's about all the models. And we're looking at how to improve performance for the important models that are really popular and every model that everyone is using in their own research use case as well. So we're looking at the whole holistic collection of models that people use on the platform. And we're looking at how to make them all better by making framework-level changes. And when we talk about performance, we're not talking about, in this case, accuracy or quality measures. We're talking about performance in terms of system performance. This means doing things like throughput, doing things like efficiency. How can we do the same using less resources and being greener and less carbon emissions? And we're also talking latency. How can we get back to the user faster with an answer and give them a more interactive experience? And we're also talking about things like throughput, where if you have a background job churning through a lot of data, how do we get those bulk collection and analysis jobs running efficiently? Performance is a difficult problem, and there are a lot of challenges that come up when we talk about performance. One of those things is understanding what part of performance is influenced by the way the user is using the framework, and what part of the performance can come from the framework itself. Because there's some things a framework just can't improve. Things like if the disk is too slow to saturate a GPU, there's not a lot PyTorch can do about getting a faster disk in place. But there is a lot of things PyTorch can do on like the fusion levels, on the way we dispatch and order operations, and that can greatly influence performance across a wide variety of users. Another challenge we look at is prioritization. Because there are so many different models, and the popular models change month by month, year by year, understanding how to prioritize what models we're working on and what models need the most performance improvement is a challenging problem. And we'll talk more about how we can do this later. Finally, we also have to talk about the quality of our proxies. This means that if the benchmark gets faster, or if the thing we're using to measure performance is faster, does that mean performance is actually getting faster for our users, for the people who are using PyTorch? And this is a really difficult question to answer, because if you're running a model in isolation on your own system, it's not always obvious if those improvements will translate to the users in their actual environments. So we're going to dig into kind of these challenges and how these can be addressed. Another set of challenges in this space comes from making sure the benchmarks are high quality, as we talked about good proxies. So certain models like recommenders, for example, the data will influence how memory is accessed during training. Other speech models, for example, may have algorithms that do searches, and depending on the nature of the data, the actual search depth can change from run to run. Also, in measuring performance and understanding performance, noise is a huge factor. For example, if we make a change to PyTorch and we want to understand, is that change good for PyTorch? Is that improving performance for users, or is it regressing performance for users? Our noise, or basically the variance from run to run of our benchmarks and of our performance measurements, dictates the smallest improvement or regression we can detect. So lowering noise allows us to detect smaller improvements and detect smaller regressions. The other big challenge that we run into when understanding performance is the configuration. You can have the same model, and you can change shapes, and having new shapes in that model can greatly influence the performance and give you an entirely different profile for how the model is performing. So just because you're optimizing, a transformer and you're trying to make PyTorch faster for transformers, for example, that doesn't mean that, because your transformer is getting faster, everyone's is, because people are using different shapes, different sizes, a different number of layers. And so we have to account for all this when improving performance. This is where Torchbench comes in. Torchbench is a new benchmark suite that we're releasing in open source that captures models the way users use them. This means running at the precisions they're using, running on the hardware they're using, and running using configurations that they are using, taking code the way it's written. And this is really important, because if you have a production system created by 100 engineers powering large products, the code will be written in a very different way than if you're a researcher working on a paper. And so Torchbench is focused on the researcher use case, capturing the code the way the researcher would write it, and capturing on the hardware they'd be running on, at the precisions they'd be running at, and making sure we have to take a holistic look at both training and inference, including eager and scripted modes. And the idea here is that we want to make sure that we have plenty of models so we don't over-specialize. We're not here to improve one model. We're not here to improve just a single model. We're here to improve everyone's models, which requires a wide diversity of models. And it also means we need to bring together the scores of all these different models to understand the impact across this very large suite. So we have a way to compute a score through geometric meaning, and we have all sorts of different configurations from all sorts of different models written as a researcher would write them. And this gives us the most accurate view possible into, if we make a change in PyTorch, how will users actually feel and experience that change in their work, in the workloads they run. So for Torchbench to be successful, as I said before, diversity is key. We want to make sure that we represent models that everyone wants to use. And this is a tricky problem because there is such a large variety of models, and it's not always obvious what's up and coming, what we should be benchmarking, what's important. So we have to be very careful about these decisions. And so the way we're approaching this right now is we take popular, well-known models that we see a lot in the community, and we bring them together. And here you can see a distribution of roughly how these distribute across different workloads and different domain types. Now, don't be alarmed at the proportionality, because as I said before, we have scores that help us normalize. So just because that we're disproportionately representing convolutions in the actual aggregation, because we can rebalance and reweight the scores we're getting from these to proportionally reflect everything evenly instead of based on how many models we have. Now, this also raises the question of how do we select models? What goes into choosing a model, and how do we know which models to use? And this is how it all works together, because anyone can contribute a model, and we don't have to worry about having the right exact proportion of models in the suite. We can take whatever models people care about and then do the rebalancing at the score level. And I'm going to talk more later in more detail about bringing in more new models. This is actually the central element of how to build a strong performance ecosystem. As I said earlier, proxies are critical. We have to know that when we are improving a benchmark, that it's improving the actual user who's using the benchmark, that someone's life is actually getting better. And this is where choosing the right benchmark code is critical. The number one way to know, is it worth improving a benchmark, is to have been given that benchmark by someone who says, this is a workload I care about. I run this every day, or I run workloads like this every day, and they actually give it to us and put it in the hands of PyTorch developers everywhere. As they change PyTorch, they can see if their change is regressing the performance of that model, and they can dig into that model and ask the question, how do we improve our performance here for everyone who runs models like this one? And this is the heart of a good, strong benchmarking ecosystem, where the benchmarks are actually sent in by the users. And so developers don't have to question, is this benchmark real or fake? Is this benchmark important or not? Because you know it's important, because you know someone told you it was important and put it in your hands. And this is our long-term goal for Torchbench. Starting out, we did our best guess at what models are important and what models people care about. Going forward, we want people to actually tell us what they want to see improved and have the benchmarking decisions driven by users and make this direct connection between users and developers for performance. So that way we know that we're actually impacting real people in real workloads and not just synthetic numbers on a dashboard somewhere that we wonder, does anyone actually care about it? So Torchbench is open source and available on GitHub. So if you want to learn more about this, you can go to GitHub, you can download and run Torchbench, and it's completely open source. In your own development, you can use it to do testing and debugging of your changes to understand if you change something in PyTorch, how is it affecting the performance for our users? And if you're a user of PyTorch, if you run PyTorch every day and you care about how fast it can get back to you with an answer, there's a simple way to add new models there. So you can open an issue or open a pull request where you bring in a model, simple interface, or point us at a model, because we'd love to just get pointers to models you care about. And we're happy to help you onboard them. And we can actually bring in these models into Torchbench and start this feedback loop between the users who use PyTorch and the developers who develop PyTorch performance. Thank you.
Hello everyone and welcome. My name is James and I'm a software engineer on the PyTorch team working on Torch.fx. Today I'm going to be introducing Torch.fx, a new program transformation system we have developed for PyTorch programs. So a little bit about the agenda today. First, we're going to cover some background. What are program transformations and why do we need them? Second, I'm going to cover the motivation of Torch.fx. Third, I'll give an overview of Torch.fx and show you how you can use it in your PyTorch workflows. Finally, I'm going to present a case study of the different use cases folks in the PyTorch ecosystem have found for Torch.fx. So first, let's start with some background. Why do we need program transformations? PyTorch's Python-based API is great for code authoring. It allows you to use the flexible and friendly Python language and allows you to access the entirety of the Python library ecosystem. On the other hand, sometimes we want to use PyTorch code in a different way from how it was authored in Python. Examples of this include model quantization, applying optimizations to the code to make it run faster, or moving the code to a specialized accelerator. These transformations often need to see the code in a form other than the Python code. Historically, deep learning frameworks and compilers have consumed graph representations of programs for such transforms. In summary, we would like to have a system that can allow modifications to PyTorch programs after they have already been authored. So how can you do such transformations in PyTorch today? One option is to swap modules in the NN module hierarchy built into PyTorch. This works in many cases, but sometimes the module boundaries do not line up with the places that you want to transform. In addition, you cannot transform code within the forward method with this technique. This includes calls to PyTorch operators, which are functions rather than modules. A second technique is to use TorchScript. TorchScript can be used to capture a graph representation of the program, including the operators, and this graph representation can be modified to implement transformations. On the other hand, TorchScript is optimized for serialization and deployment, so the way it represents programs is very complicated. Its representation supports many Python features and is optimized for use by experienced compiler engineers, so it is often difficult to use for many developers. So there are existing techniques that you can use to modify programs in PyTorch, but we've built Torch.fx to make this process even easier. Let's dive into that. With Torch.fx, we want to provide a system that enables capture and transformation of PyTorch programs after they have been written. We strive to follow a few principles in the design of Torch.fx. First, it should be Python native. It should consume and produce Python programs, and its APIs should be written in Python. Second, it should be simple to use. It should provide a simplified program representation and simple APIs for the end user. Finally, it should be lightweight. The user should be able to use Torch.fx with their existing PyTorch installation. The user shouldn't have to learn or compile C++ to use the system. So let's cover what Torch.fx actually is and how to use it. Torch.fx has three main components. First, it has a symbolic tracing mechanism to capture the program. Second, it has an intermediate representation, or IR, that is a data structure that represents the code of the captured program. Finally, it has Python code generation to return this IR back to the Python ecosystem. This is the typical pipeline used in Torch.fx, but each of these components can be used separately as well. Torch.fx uses a technique called symbolic tracing to capture the program. It feeds fake values through the program and records the operations that happen on those fake values. You can see in the code example to the right that the fx.symbolictrace API exposes this functionality. Just pass in a function or module to this API, and fx will capture it using symbolic tracing. Note that symbolic tracing only supports DAG programs, that is, dynamic control flows such as loops or if statements that depend on dynamic values are not supported. Neural networks are most often DAG programs, so we find this is a reasonable trade-off, as it simplifies the graph representation for transformation purposes. Nevertheless, symbolic tracing is configurable via the tracer class. A custom tracer can be used to specify the level of representation of the capture, or leave untraceable parts of the program as opaque calls and allow the program to be captured. Once a program is captured by Torch.fx, it represents the captured operations in a directed graph or DAG representation. This representation records the functions, modules, and methods called, and the data dependencies between them. Nodes in the DAG are the operations, and the edges are the values. This DAG representation has convenient APIs to add, remove, reorder, or replace operations, allowing you to transform the code as you please. You will see on the right a string representation of this graph structure, containing the ReLU and neg operations that were observed during tracing of this function. Finally, torch.fx provides Python code generation from this IR. You will see on the right the code that is generated from the IR we saw previously, similarly containing the ReLU and neg operations. Since torch.fx emphasizes interoperability with Python, transformed programs are returned to Python through this mechanism. Transform code is wrapped in an NN module subclass called GraphModule, and the generated code can be called just like any other NN module instance, or passed to other systems such as TorchScript. Now let's take a look at a few of the use cases folks have found for torch.fx. First, torch.fx is being used in the prototype FX Graph Mode Quantization tool. Torch.fx provides the ability to programmatically modify the operations and the parameters of a model, so it is a good fit for quantization, which modifies both. Second, torch.fx is being used for optimizations such as fusion and operations scheduling. FX can be used to, for example, fuse convolution and batch norm operations together, or schedule asynchronous versus synchronous or local versus remote operations for maximum parallelism. Third, torch.fx has been used for various analyses. These include analyses like shape propagation or inference, or model simulation to determine the performance characteristics of a model without using actual hardware. Finally, torch.fx is being used for device lowering to optimize model execution on various hardware devices and in optimizing compiler backends. What will the next use case on this list be? Will it be yours? Please check out our documentation at the link to the right and try out torch.fx for your program transformation needs. And please feel free to ask questions on the discussion forums or report issues on the GitHub issue tracker. Thank you.
Hi, I'm Michael. I'm a software engineer on PyTorch Compiler, and I'm here to talk about our journey enabling PyTorch Eager for production audiences and large-scale production users. So I'm going to cover three major topics in this talk. The first is why Eager? Why are we building an Eager mode integration for our production audiences? The second is what are some of the key technical challenges that we faced when trying to bring Eager to production audiences, and what we built to help solve or resolve some of those technical challenges. And the third is bringing back compilers and optimization into an Eager-first world. So why Eager? The chief goal that we wanted to accomplish was to bring the full flexibility of PyTorch to production audiences without any compromise. So people love using PyTorch because it has a very Pythonic look and feel, and they feel they have the flexibility to do anything necessary to experiment with their ideas. And we wanted to bring that experience to a full production stack. And so we wanted to make it so that any wild thing that you can do while developing a PyTorch model, you should be able to bring directly to your users without too much additional work. So today, the most common path for production users is to write their model in TorchScript and deploy it using our TorchScript runtime and JIT compiler to a large-scale C++ inference service. And in the name of being a really solid and portable and robust production framework, TorchScript makes some pretty clear design choices, right? The TorchScript language subset is a statically typed subset of Python. It's focused on providing sort of high performance representation at the expense of some of the dynamism and flexibility that we know about from PyTorch. And this works. TorchScript itself is now widely used across the industry, both at Facebook and other places, in large-scale inference services, on mobile phones, in autonomous vehicles, and all sorts of places. But As we progressed further into our research to production journey, we found ourselves talking with a number of production users that were struggling to fit some of their more dynamic or more flexible models into sort of the TorchScript static regime. And here's an example of one of them. So we spoke to a group that's trying to deploy a library called Captum to production. So Captum is a library that provides model interpretability algorithms for PyTorch models. So it basically explains why a certain classification was achieved. In this case, you can see in this picture that it's like an image classification algorithm, and it's explaining, oh, why did I think something in this image was a monitor? Or why did I think this was an image of bottles? And they wanted to be able to show their users, why some of their images were classified in a certain way. So far, so good, but the issue is that Captum itself makes extensive use of this full range of PyTorch features available. There's a lot of dynamism. For example, they call backwards and they add, a backward hook dynamically in order to observe gradients as the backward is executing. And this is something that TorchScript simply can't represent. They need the full flexibility of PyTorch Eager in Python in order to actually bring this model to production users. But at the same time, this group was operating at scale. They ran a large C++ inference service that looked like the usual inference setup, right? It's C++, high performance RPC server, shared memory multi-threading, and they couldn't deploy Python directly to that service because you can't achieve parallelism with multiple Python interpreters within the same process. And so TorchScript was solving a very valuable problem for them. It let them embed the model inside their inference service in a parallelism-friendly way. But they were struggling with the fact that TorchScript, the representation or the packaging format couldn't fully capture the model that they had. So that brings us to what we built, in an attempt to address some of these issues. So talking to production users like the Captum folks, we realized that there are 3 distinct requirements for a production system or a research to production workflow. The first is packaging. We need a way to bundle up and distribute PyTorch models in a hermetic and reproducible way. The second is deployment. We want to be able to integrate any runtime that we have for running these models into an existing production setup. And we want it to be compatible with a wide range of production setups. Everything from a Flask-based Python web server to a high-performance C++ RPC stack, right? And the third is optimization. Once we have these models and we're running them, how do we make them as fast, as resource efficient as possible so that we can scale up this model for production use cases? So with TorchScript, it was sort of an all-in-one solution, right? You saved your model with torchzit save, which would save it to the TorchScript serialization format, and you ran it in the TorchScript runtime. And while you were running it in that runtime, we had a TorchScript JIT compiler that would go in and optimize your code. And this works really well, as we've seen, but for some users like Captum, they were struggling with the fact that for packaging and deployment, they needed to export to the TorchScript language subset, which impose a set of constraints like static typing and no dynamic behavior on everyone, regardless of whether they were performance sensitive or not. As a result, we decided to unbundle these components into a modular toolkit for research to production. So for packaging, we have Torch Package, which is a sort of Python native packaging format that allows you to take arbitrary Python data and code and put it in a hermetic and reproducible container. We have Torch Deploy, which lets you run an eager process from a variety of production contexts. And for optimization, TorchScript isn't going anywhere. You can still use TorchScript to optimize the parts of your model that you need to. So let's start with Torch Package. This is a library that allows you to bundle model, weights, and code together in a pure Python way. So as you can see, you can export your model by saving it in a pickle-based format. You can save arbitrary code, and then you can load it back up. And a key difference between Torch Package and already existing ways of saving models is that, for example, when you pick a model today, you mostly are saving the state dict, the parameters and buffers, and not the actual code that the model depends on. This means that depending on which environment you load it from, the model behavior could be different. So the way that Torch Package works is that it actually detects the dependencies of your data and packages all the code necessary to reproduce the model and load it from any environment, regardless of what version of the code you have in that environment. And Torch Package is available as a beta in the latest release of Pytorch. So if you have a package model, how do we actually run it in a C++ or a large-scale inference service with Python? So that's where Torch Deploy comes in. So for that, we have Torch Deploy, a library that allows you to run multiple embedded Python interpreters within a single process. And here's a code sample. As you can see, calling the model is like calling into any C++ library. There's no special setup, and most importantly, there's no weird interaction between the embedded Python interpreter and any global state that may inhibit parallelism. So we're really excited about this technology because Python's so-called global interpreter lock, which prevents concurrent execution of Python bytecode, has been one of the key technical challenges to deploying Python for machine learning at scale in some of these production contexts. And we think that this technology helps address this challenge and unlocks a lot of potential for running pure Python for research to production use cases. And Torch Deploy is experimental in the current version of Pytorch. Now, that doesn't mean that it's unstable. It just means that the APIs are subject to change as we refine them. And of course, TorchScript is still in the mix, right? For users who benefit from TorchScript's all-in-one approach to packaging, where you package the model and it's in a very portable embedded format that runs on a specialized interpreter. Examples might be PyTorch Mobile or running PyTorch in embedded environments or on a car. They can continue to use PyTorch just as it is today. But for server use cases that want to push boundaries in terms of what kinds of models that we're running and the flexibility and dynamism of those models, we expect TorchScript to be more used like a paintbrush than a paint bucket, right? You're going to optimize the specific parts of your program that you think can be accelerated or benefit from optimization, but more tricky or complex or dynamic code can just be run in Python. So we hope by doing this, we can provide a really seamless end-to-end research to production workflow. You can start by directly exporting your Python code to run in a high-performance parallelizable setup while optimizing it as needed with TorchScript. Lastly, I wanted to zoom in on optimization and performance as it applies to Eager in production. So in the August 1983 edition of Byte magazine, Stephen Johnson and Brian Kernighan were making the case to a skeptical audience for writing programs in their new high-level expressive programming language. They argued that iteration speed and flexibility trumped raw performance, not because performance wasn't important, but because you could always go back later and add performance. That's the idea behind make it work, then make it right, then finally make it fast. I mean, the irony of this case is that this high-level expressive programming language they were talking about was C, but I think it applies just as much to machine learning today. They apply well to our current context, and the reason we want to enable Eager in production is so that folks can make cutting-edge research and cutting-edge models available to people as quickly as possible, and then go in and incrementally optimize for efficiency and capacity purposes. So a really important part of basing our research to production workflow on Python is that Python is the lingua franca of numerical and scientific computing. So like every optimization or compiler project under the sun has bindings to Python, and you can use them from within our system. So we really want to emphasize people using the right tool for the job. And the projects listed here are just examples, right? There are many, many other things that we didn't put here, but If you need to use TensorRT because it's the best fit for your workflow, you can, because we sort of have this common deployment platform that's based on Python, and everything has bindings to Python. So looking forward, we want to bring a mixed eager and graph mode execution model to PyTorch, to general PyTorch audiences. And that allows us to provide a sort of bridge from PyTorch eager execution to domain-specific compilers without users having to do a lot of work to explicitly invoke these tools. And this is all kind of rolled up under the idea of a lazy tensor. And we have a lot more exciting work going on in this area, so stay tuned for more details. And so overall, the way that we view the future of compilers in PyTorch is we want to emphasize using Python as a basic substrate, a lingua franca, with a modular compilation optimization stack that lets you use the best tool for the job. And at the same time, we'd like to really enable and push on lazy execution within PyTorch to provide a bridge between more static domain-specific compilers and Pythonic eager mode developer experience. All right, thank you.
Hello, my name is Kyuk Chung. I'm a software engineer in PyTorch's Research to Production, or otherwise known as the R2P team. Our main goal in R2P is to make PyTorch a delight to use in production. Today, I'm here to present to you a project called TorchX that we open sourced recently, specifically for this purpose. In short, TorchX is an SDK for quickly building and deploying ML applications from research to production. It enables this in 3 very easy steps. The first step is to define or choose a component. A component is just a fancy term for a flexible job specification. The class definitions for a component are defined in the TorchX specs API, but in most cases, you actually won't have to worry about defining your own components, since TorchX ships with a set of built-in components that suffice most use cases. But should you need something more custom, TorchX's core APIs allows tons of customization at well-defined extension points so that even the most unique production applications can be serviced without customizing the whole vertical stack. Once you've defined or chosen a component, the second step is to see the component in action by running it as a job. We realize that adopting a new technology in production takes development resources. And the good news is that you can get started with TorchX at no added infrastructure setup cost. This is because TorchX works with popular ML schedulers and pipeline orchestrators that are already widely adopted in the industry and deployed in production. So chances are you're already running a scheduler that TorchX supports. Lastly, production jobs often run in the context of a pipeline or a workflow with both upstream and downstream dependencies. So for example, a training job may have to wait for data to arrive, and similarly, inference has to wait for the latest trained model. TorchX components can be converted into pipeline stages of a supported ML orchestrator and run as a stage in existing or new workflows. In the next 3 slides, let's take a look at each one of these steps in more detail. A component in TorchX is a Python function that returns a well-defined job specification called an appdef. An appdef is a Python data class that holds all of the necessary information to run an application as a job. Let's take a look at some examples. On the right-hand side are 2 components, train and train dist. Both train and train dist are Python functions that take parameters and returns an appdef. Train specifies a single node job that runs the entry point my/trainer/main.py in a container created from image my/docker image. Additionally, it sets environment variables, rank and role size, to 0 and 1 accordingly. And it also requests that these containers run with resource requirements equal to those of a P3 8x large instance type on AWS. On the other hand, train dist is a distributed data parallel version of train, where we ask the scheduler to run n nodes number of containers, each container running n proc per node number of trainers. But unlike train, rather than spelling out the appdef, it's using a built-in dist-DDP component. This makes things much more concise for train dist, despite the fact that it is actually asking the scheduler to run a more complicated job. The concept of components exists in TorchX because components essentially parameterize an appdef. The parameterization criteria is completely your choice. For example, you can parameterize components by functionality or by development stages. In train dist, we decided to parameterize the built-in dist-DDP only on the job size, while hard-coding the entry point, image, and host type. Built-in components such as dist-DDP, serve, and HPO can be composed into custom components or run out of the box, as we'll see in the next slide. In the previous slide, we saw what components looked like. Now let's take a look at how components are submitted as jobs. The TorchX runner is responsible for submitting a job given a component. And at a high level, the component is evaluated to obtain an appdef object. The TorchX runner has integrations to popular schedulers like Kubernetes and Slurm, and it also includes a local host mode to help you quickly iterate on your components and applications on your local dev desktop. It's also easy to add a custom scheduler by implementing a few methods in the TorchX scheduler interface. The two CLI examples on the left-hand side show how to run the custom train dist and built-in dist-DDP components from the previous slide. And notice that the list of arguments we pass to the components are different since they're parameterized differently. Dist-DDP is more generic since it takes the image and script as parameters, whereas train dist is less flexible but simpler. The -s Kubernetes option tells TorchX that the components are to be submitted as a job onto a Kubernetes cluster. To run the component on different scheduler, all you need to do is to pass a different -s option. So for example, to launch on Slurm, you would pass -s Slurm instead of -s Kubernetes. It's also without saying that in addition to the CLI, there's a programmatic API to the TorchX runner, so that you can build custom programs that launch components. So finally, we get to pipelines. And the production story wouldn't be complete without talking about how to run components as part of a larger workflow or pipeline. In TorchX, you can convert your component into a pipeline stage by using the TorchX Pipelines adapter. Just like the runner does with schedulers, pipeline adapters in TorchX support existing mainstream pipeline orchestrators. Once you've converted the TorchX component as a stage in the target pipeline's DSL, you can go about defining the workflow purely in the pipeline orchestrator's language. The example on the right-hand side shows how a TorchX component can be plugged into Kubeflow Pipeline's workflow. First, the appdef is materialized by evaluating the component function. Next, the appdef is converted into a KFP op using the component from app method from the TorchX Pipeline's KFP adapter module. The DAG itself is purely defined in Kubeflow Pipeline's lingo. A nice side effect of this design is that you can plug in TorchX components into existing legacy pipelines, which reduces the cost of integration since TorchX components can be used with existing legacy pipeline ops. And with this, we've covered the three basic steps to start using TorchX in production. 1, define or choosing a component. 2, running it as a job. And 3, converting it to pipelines. So hopefully you got a good sense of what TorchX is and how it can help accelerate research to production for your organization. We've open sourced TorchX 0.1 with a collection of MVP built-in components, schedulers, and ML pipeline orchestrators. And we hope that with your interest and contribution, together we can build a vibrant production ecosystem for PyTorch. Thank you.
Hi, my name is Lawson Huang, and today I'd like to share some insights from our real-world research to production work from doing projects in machine learning at Fidelity. First, I want to give an overview of how we see machine learning use cases changing in recent years. And there's been a shift in what machine learning use cases look like now versus, say, 2 or 3 years ago. The second, I want to talk about this idea of model development without labeled data. So you often hear these stats like 90% of machine learning projects never make it to production. And I suspect one of the reasons there's multiple reasons for that, but I suspect one of the reasons for that is that oftentimes a machine learning team will hit a point where they say, oh, well, we don't have labeled data, therefore we can't move forward. And I want to kind of share some strategies to kind of expand the scope of what do you do in that context, or what are some strategies there. Third, I want to talk about kind of an end-to-end view of how your machine learning model gets embedded in a broader application, and what are some of the things that you think about even as you're kind of developing the model. So first, I want to acknowledge my team here, who are really kind of the ones that brought our machine learning projects to life and helped me kind of learn some of these things as we tackled our projects on a day-to-day basis. So first, how are machine learning use cases changing? In the past, when you saw discussions of machine learning systems, you always see this figure of this kind of production ML systems discussion. And it's oriented toward this idea of machine learning as a prediction engine. So there's a focus on feature-based prediction. You have these complex data cleaning pipelines that are replicated in development and production. And you think about machine learning as these kind of big data batch inferences going through these pipelines. Recently, I think you see more and more projects that take a different shape to them. Rather than just being prediction engines, they're sort of generalized perception engines. And I mean that sort of beyond machine learning and robotics and other things, but really kind of perception in the sense that the role of a machine learning model is to shift the boundary of what you can compute on. So to enable you to compute on text through NLP, enable you to process images through computer vision, and these sorts of use cases. So in these sorts of use cases, you often see noise becoming part of the data distribution for the model to reflect, rather than something that's upstream of the that's sort of cleaned up upstream of the model. You also kind of have this shift from pipelines to real-time low latency APIs. Now, these two categories aren't necessarily either or. You can always wrap an API and kind of put that into a pipeline process. But there is kind of this shift in trend of what sort of problems are being tackled that we've seen, at least. And so systems that have this sort of shape to them look a little bit more like this, where you have a set of tools used for model development, including data, sort of things to transform data and augment data. And when you've trained your model, you then deploy it by taking, say, like a serialized version or the final version of your model and embedding it into some sort of service API that is the kind of the production interface to the model. Furthermore, there's some sort of consumer of that service. It could be just a client, or it could be a web or mobile app, or it could be some sort of embedded system if you're in the realm of robotics or autonomous driving. Now, the model can also be serialized and potentially run on the edge, right? And finally, there's an aspect of feedback that you want to sort of capture data that then goes back into your data sets to improve your models, right? And so these kind of use cases tend to take on this sort of shape, including our own. So for example, we develop a neural retrieval model that basically enables in our app for young investors for people to type in some piece of text about what they're looking for, and then it returns some combination of content and also in-app places that they can go to that are relevant to what they typed in. And here, so you have sort of the edge client being the mobile app, you have API services that support that, and you have a model that's basically serialized and then embedded into the API service. Another example is for document automation, where we use vision and sort of multimodal models to support document automation, either categorization, text recognition, and detection of things on documents. Finally, you have internal tools to deal with text that our internal colleagues may use to process financial documents, process their notes, and so on. So each of these, you have kind of that model, you have kind of a deployment API, and you have kind of an integration with some sort of consumer. So what I want to talk about next is how do you go about developing these models? In all these use cases, we often start without any labeled data. So how do you approach a project when you're in that context? So this may be this is a view of maybe kind of the traditional view of how we think about supervised learning. And nowadays, often you start with some sort of pre-trained model, and maybe kind of the supervised component is to fine-tune that supervised component. But you're still relying on potentially a large number of labels, especially if you're dealing with unlabeled data. It may take quite a bit of labeling before your model behaves the way you want. We often find what succeeds is to get as far as possible using programmatically generated label. And that could be labels. And that could be using sort of simulated data or using some sort of auto-labeling strategy. And really kind of the manual labeling is just that last kind of 5-10% to go from the approximation that the baseline gets you to the details of the specific intent that you're trying to achieve with your machine learning model. So one example of this is this project Sim to Real Docs, which was accepted to this year's NeurIPS Data-Centric AI workshop, where we basically programmatically control a Blender renderer. Now, Blender is basically an open source tool that can do ray traced rendering, often used in, say, visual effects or film. By programmatically controlling it, we can basically produce ground truth, kind of like 3D renders of documents under natural scene conditions. Why would we want to do that? Well, nowadays, when documents tend to come in from mobile apps mobile app photos, more so than someone actually bringing a piece of paper to a branch and then that being sort of scanned on a high quality scanner. So you need your all your models that are doing recognition, detection, classification to basically function correctly under these conditions. And by using simulation, we can produce ground truth and we can do domain randomization to make those methods robust to these sources of variation. Second example is for NLP use cases, you can often use auto-labeling strategies. And the advent of these kind of high-capacity, zero-shot models that you can design prompts to have them function, do an approximation of what you're trying to achieve is a very powerful tool there. So you may start with unlabeled data and you take a zero-shot model, something you can design a prompt to do what you want, say approximate the text class that you're trying to achieve. Now, a lot of the zero-shot literature kind of stops there. That's kind of the end point of the model. But for a kind of a real-world project, you don't actually want to deploy your zero-shot model because it's not 100% sort of capturing what you want the model to do. So you can insert human annotators at this point, and they can either sort of just correct the labels, which correcting is a lot faster than labeling from scratch, or if you're willing to sacrifice some degree of recall, they can just correct the positive labels. And then you can take that data set that's been corrected and use that to, say, fine-tune a student model. The student model can have lower capacity because you want it to be lower latency, and you're also trying to deploy something that is a fit for purpose task. So you don't need all the generalizability of those teacher models. So this could be something like a BERT or a distilled BERT model that then you fine-tune on this data and you deploy. So these are some examples of cases where we have projects we start without any labeled data. And you think about part of the skill and success of these projects depends on your ability to think creatively about how do you generate some data to get to a baseline and then tweak that to get to your final model. So I've talked about training. Next, I want to talk about sort of these end-to-end considerations of your model and how it's integrated with your use case objectives. right? And it used to be that if you were a model developer, kind of your primary concern was you get to, high test accuracy. And after that, everything beyond that is someone else's engineer's job or the designer's job to kind of put it into production. And I want to kind of flip that a little bit, right? And think about, as model developers, there are things you can kind of consider from an end-to-end perspective that are worth thinking about if you want projects to be successful. And one inspiration here is Brett Victor, who has a lot of ideas about how to make tools effective. And one quote he has here is that there can't be a delay and there can't be anything hidden. And what he means by this is that if you're creating a tool for someone to use, that any delays kind of get in the way of how a person interacts with that tool. And any sort of hidden state confuses the user in terms of what's happening, how to use it. So even though he's not talking specifically about machine learning, we find some of these ideas apply very much in machine learning use cases. So this idea of speed comes up in terms of the inference latency of your model. And so here you see on the left is the experience a user would expect. And on the right, if your model inference latency is too high, you simply can't use the model for this use case of a user experience in a mobile app. And that just means it doesn't matter how accurate your model is, it's just not going to be successful. And we've already talked about kind of one example of how you can kind of design your model of human-in-the-loop distillation, where you can kind of think about that from the way you design your model training to have low latency in mind. Another kind of direction that we've explored is with sparsity optimizations. It's not just that you have to kind of apply sparsity procedures, you actually have to have runtime support. So we had a paper earlier this year where we're seeing that if your runtime can support sparsity optimization, there's potentially a lot more headroom for even more speed up in inference latency than what we typically see with kind of the current procedures for machine learning compilers. And of course, you should always take advantage of compiler tools like TorchScript, Onyx, and TVM. Often even just sort of using them off the shelf can get you a 2x or more improvement without that much work. So the second thing, just as sort of latency is not just purely the domain of your production engineers, same thing is worth kind of thinking about design even as you're developing your model. So let's take this example of text classifier. For as an internal tool, you might want that text classifier to feed into a user interface where maybe when a classification shows up, it shows up as a button or something, or as something that the person can interact with. So you need to line up sort of your prediction heads so that it corresponds to those user interface elements, right? And just as Brett was saying, you don't want things to be hidden. Maybe you want to track kind of data as it goes into your model so that when someone presses the button, they can see the underlying text that was classified. And you may want to go beyond that, and maybe you want your model to show what passage of the text led to the classification. And that may lead you to add, say, like a span prediction output as part of your model. So here's just an example of kind of how these kind of end-to-end considerations of how you want the user experience to be kind of changes the way you architect your model and what you're training for. Another kind of example, kind of coming back to this neural retrieval example, where your input is a text box for someone to type in what they need, and you want that to drive a user experience to show different pieces of content or shows kind of different deep links within the app that are relevant to their query. So here you have kind of two inputs to the model of the content and the query itself. And then you also have the client side piece of this. So on the edge, it has to know how to interpret your model output and then render that into a particular view. So deep links might appear a certain way and content looks a certain way. So in these cases, it's really just kind of reflects this kind of thinking about, you're kind of thinking about how your model gets used beyond test accuracy and sort of planning for what the ultimate sort of experience or functionality of your model is, right? And one kind of first kind of order way of thinking about this is that your kind of inputs and prediction heads are interfaces between your model and user interface. And I think beyond that, we need more of a new design language for thinking about how machine learning and experiences interact with one another. Second is how inference latency can make or break whether your project is successful. And it's kind of useful to think about that even when you're doing model development. And there's probably opportunities for compiler optimizations that go further into that sort of modeling side of things and think about sparsity and distillation as potentially like a compiler step of a model. Second, another set of takeaways is we talked about kind of data synthesis and auto labeling, and really to kind of get out of this mindset of because you don't have labeled data, you can't move forward. And part of the skill of developing models is to create sort of programmatic ways of generating data and using that to bootstrap your model development. And finally, we observe this kind of broader shift in kind of how machine learning is getting used, from these kind of batch big data sort of prediction engines to being these kind of perceiver capabilities that are expanding the boundaries of what sort of data that you can compute on. And so with that, I'd like to wrap up. These are a few pointers to some related papers. And feel free to get in touch with me if you're interested in discussing real-world machine learning in the future. Thanks for your time.
Welcome everyone. My name is Geeta Chauhan and I lead the PyTorch Partner Engineering at Meta AI. Today I will be talking to you about TorchServe, the PyTorch Model Serving solution. Deploying and managing models in production is difficult. Some of the pain points include ease of use for loading and managing multiple models on multiple servers or end devices, running pre-processing and post-processing code on prediction requests and still have a high-performance solution. How to log, monitor, and secure predictions running on-prem or in the cloud. What happens when you hit scale? Can you do this in a cost-efficient manner? We launched TorchServe for PyTorch Model Serving with AWS last year to address these challenges. It comes with the default handler for common ML tasks like image segmentation, text classification, and a model zoo to quickly get started. One can create their own custom handlers. There is a robust management, inference, and metrics API. It supports dynamic auto-batching, versioning, rollback, and common metrics for performance tracking. TorchServe has now evolved into a multiple platform solution across AWS, Google Cloud, Microsoft Azure, and the major open source platforms like Kubernetes, MLflow, Kubeflow pipelines. Some of the recent features include ensemble model support, Captum integration for model interpretability, Kubeflow pipeline support for the open source Kubeflow pipelines and the Google's Vertex AI pipelines, model signature support for the MLflow deployment plugin, AWS Inferentia support for accelerated computing, Canary deployments and autoscaling, and new examples for MMF, neural machine translation, DeepLab v3, faster transformers. We added the new workflow feature for ensemble model support, which includes the parallel and sequential pipeline along with the new workflow archiver container for deployment. And we provide examples for neural machine translation and computer vision to get started. This is the dual translation example. On the left-hand side, you see the YAML configuration file describing the DAG for the pipeline for converting to German and French. On the right-hand side is example of the code in the workflow handler, and below that the torch workflow archiver command for generating the package. On the metrics side, we added a new example showcasing how to define your own custom metrics. Here, we are logging the size of the image and then using Google's MTail tool to process the metrics and show them in Prometheus and Grafana. On the MLflow side, we enhanced the deployment plugin to add support for model signature validation. You save the schema at the time of the save model and then use it in the TorchServe handler for validation. For model interpretability, Captum has been integrated. You override the getInsights method with the attribution code, and we provide very good examples to get started on the NLP and computer vision side. If you need full customization, you can override the full explain handler, and these examples for these are available in the MLflow deployment plugin and the Kubeflow pipelines repos. We recently integrated PyTorch with the Kubeflow pipelines for the end-to-end model training to deployment to monitoring solution, where we use the KF serving for the model serving side. KF serving has now moved under the Linux Foundation with a new name, Kserve, and it uses TorchServe for the PyTorch model serving and provides features like canary rollouts, autoscaling, log aggregation. On the right-hand side, you see the actual execution flow with the profiler output, and at the bottom, the Captum interpretability results. We collaborated with Google for integrating the KFP pipelines in the Google's fully managed serverless pipeline solution, the Vertex AI pipelines. It provides the end-to-end model training, deployment, and inferencing. There are predefined ops for TorchServe model serving, including the model upload, the endpoint creation, model deployment. It supports both CPU and GPU deployments. For canary rollouts, you can use the traffic splitting feature. and all the ML metadata is tracked using the artifact lineage tracking. So you start off by defining your pipeline. You will do the pre-processing, you will train your model. Once your model is ready, you will generate the MAR file for deploying on the TorchServe side, and then build the TorchServe image. You invoke the model upload op for uploading the model serving container, then call the endpoint create op for creating the endpoint, and finally call the model deploy op for deploying the model to the endpoint, and you can configure things like accelerator type and traffic splitting. And then you can hit this the deployed model for your actual inferencing requests. Now let's look at some of the best practices for production deployments. In order to have success for your models in production, one needs to start with responsible AI and fairness and human-centered design in mind. Here you will define the measures for model skewness, data and model bias, and look at transparency and inclusivity. After the models are trained, one has to go through the optimization phase for deploying into production. This includes looking at performance versus latency considerations, using techniques like torch scripting, quantization, pruning, mixed precision training for high throughput, optimizations for offline versus real time, and cost optimizations like running on Spot instances or AWS Inferentia. For the actual deployment architecture, one has to look at whether a model will be deployed in a standalone mode with an orchestrated solution, on-prem, or on the cloud. For resilient ML services, robust endpoints need to be provided, and one has to consider factors like auto-scaling, canary deployments, A/B testing, shadow inferencing. There needs to be a continuous measurement of the right metrics of the model, performance and interpretability to refine the model over time and ensure that it is meeting the responsible AI and fairness goals. TorchServe offers a range of deployment options ranging from on-prem to hybrid cloud, and fully managed solutions. Depending upon your development lifecycle stage, you can start simple during dev testing with a standalone setup, install from source, use a AWS CloudFormation template or a Docker container or serverless functions to quickly get started. As you move into the experimentation and staging lifecycle stage, you can use MLflow, Kubeflow, deploy it as a microservice behind an API gateway, or use the SageMaker or Vertex AI endpoints. For production deployment, you can use it on Kubernetes or use the Kubeflow with the KFserve for auto-scaling and canary rollouts for deployment at scale. In the case of managed solution, you will use the AWS SageMaker or the Vertex AI with the traffic splitting feature. Now let's look at some of the examples of how people are using TorchServe. Amazon Advertising is using PyTorch-powered NLP and computer vision models for their ads review process. They use a wide variety of models like content models to detect headlines, text, background, and objects, language models to validate syntax and grammar and flag inappropriate words. The predictions run on TorchServe, deployed on AWS Inferentia chips, and they were able to get 30% lower latency and 71% cost savings with this solution. Dynabench is a research platform from Meta AI for dynamic data collection and benchmarking. You can think of this as a Kaggle platform for NLU tasks. It uses TorchServe for the model evaluation analysis. Here one uses the DynaCLI interface and provides the TorchServe model handler for scoring one's model submission. The recent Flores Low Resource Language competition was held on this platform, and results were announced at the EMNLP WNT conference in November. We have now opened up this platform for any researcher to build their own benchmarking tasks. OpenMM Lab is a popular open source project that offers a toolbox focusing on computer vision for tasks like detection, segmentation, etc. So what you see here is an example from the MM detection project, which has added integration for TORCHserve for model deployment. Please explore TORCHserve for your model serving needs and reach out to us on GitHub or LinkedIn. We can help you for any aspect of your model training to model optimization, and I look forward to hearing from you. Thank you very much for coming to my session.
Hi everyone, my name is Raziel, and I am a tech lead in PyTorch. And today I have some exciting news on the developer productivity front. As you probably already know, PyTorch's mission is to accelerate the path from research prototyping to production deployment. This is important not only to reduce the cost from taking a model into a product, but because we know both research and product development are highly iterative. And being able to loop back product feedback to research in quick iterations translates into better models for the target use case. In order to make this happen, we operate under 4 guiding principles. First, we always enable cutting-edge research, and we want to co-develop with many stakeholders. We are also modular to allow users to only use what they care about, and we are performant and production grade. This has never been more important than in the already big and growing on-device ML ecosystem, where on one hand, being able to easily go from idea to prototype on the actual target device is key to meet the more stringent resource restrictions of mobile devices. And on the other hand, we want to enable the large community of mobile developers. With the goal of reducing the friction to create novel ML-based mobile solutions, we introduced PyTorch Live. During the rest of the talk, Roman will cover the details of why exactly PyTorch Live is and how it works.
Thanks, Raziel. If you're an ML researcher or mobile developer, this is for you. I'm Roman, and I'm a software engineer on the AI Experiences team at Meta AI. Today, I will be talking about what PyTorch Live is, what PyTorch Live currently supports, what you can expect from PyTorch Live in the future, and how you can get started with it. Currently, PyTorch Live is a set of tools to build mobile AI-powered experiences, but it will continue to grow over time. These tools support building mobile AI-powered apps that run on both Android and iOS platforms. Now, instead of having to write the same app twice in 2 different programming languages, PyTorch Live uses JavaScript as a unified language to write apps for both platforms. To achieve this, PyTorch Live is powered by PyTorch Mobile and React Native. First, PyTorch Mobile powers the on-device inference. Second, React Native is a best-in-class JavaScript library for building visual interactive user interfaces for Android, iOS, and other platforms. Both are active and flourishing open source projects with tons of examples and tutorials. Here are 3 highlights of PyTorch Live. First, a command line interface which quickly sets up a mobile app development environment and bootstraps mobile app projects. Second, a data processing API which prepares and integrates custom models to be used with PyTorch Live. Third, a cross-platform API which builds mobile AI-powered apps for Android and iOS. For example, if you want to showcase a MobileNet model that runs on Android and iOS, it would have taken days to configure the project and build the user interface. With PyTorch Live, it cuts the cost in half, and you don't need to have Android and iOS developer experience. And here's how it works. Let's start with the command line interface, or CLI for short. The CLI reduces the setup costs for mobile app development and helps you to set up a mobile app project for PyTorch mobile models in just a few minutes using simple commands. The setup dev command will install development dependencies including tooling like Yarn, Watchman, and CocoaPods, SDKs like OpenJDK and Android SDK, and an Android emulator. And this is a one-time install, so it takes a few minutes depending on the internet speed and computer. Once the development dependencies are installed, the init command allows it to initialize a new PyTorch Live app project. And this project contains all native code necessary to run Android and iOS. It also includes working examples for image classification, object detection, and natural language processing. Lastly, the run Android and run iOS commands build and run the app either in the emulator or on a physical device. This is a great starting point for you to adapt any of these examples, and of course, you can bring in your own PyTorch mobile models. Now that we've set up the mobile app project, let's look at how to integrate your own models into PyTorch Live. One challenge when building AI-powered apps is the integration with data from device sensors or user input. The data processing steps are often not part of the model and need to be programmed additionally. For example, integrating an image classification model to work with the camera input requires custom data preprocessing steps to convert a 3-channel RGB image to a tensor. In reverse, the model output needs to be post-processed, returning a consumable data format such as an image class. And this would need to be done for both Android and iOS. PyTorch Live offers a cross-platform data processing specification that abstracts processing steps and makes it possible to integrate ML models on different platforms. It allows you to more easily share models with others in the community. To add an ML model in PyTorch Live, we first need to include such a data processing specification. And the specification is in a JSON format that describes the data processing steps for our model. Let me show you what that looks like for an image classification model such as MobileNet. A specification consists of two parts, a PEG definition and an unpeg definition. The PEG converts input data such as an image to a tensor. The unpeg converts the model output into consumable data. The tensor from image transforms an image to a tensor using 3 transforms: a center crop transform, a scale transform, and an RGB normalization. The unpeg definition will compute the argmax on the model output and return it as a result. The specification can also define variables, prefixed with a $, which allows you passing in params with the model call. The processing specification needs to be bundled as an extra file with the model, and this can be done during the model export in Python. PyTorch Live comes with a selection of transformations implementing best practices for image classification, object detection, and natural language processing. We plan on supporting a wider range of ML model domains and also releasing a flexible data processing API exposing functions like Torch argmax or Torch vision transforms from the C++ APIs directly to JavaScript. In this way, you can choose to include the data processing as part of the ML model or have it be part of the app logic. Now that we've set up the mobile app project and prepared a model, let's see how to use the model in an app. Building apps that work across different platforms requires expertise in multiple programming languages and therefore increases the cost to showcase models on different devices. PyTorch Live uses JavaScript, and it can be used to build apps for Android and iOS. PyTorch Live comes with a set of examples for image classification, object detection, and NLP. If your model is in any of these categories, you can plug and play your model without the need to program a user interface. But you can also build your own user interface to showcase your model. On top of basic user interface components from React Native, PyTorch Live provides a camera component for image-based ML model use cases, a canvas component to give you the flexibility to draw primitives, for example, drawing bounding boxes around detected objects in an image, or creating freeform drawing canvases to feed drawings into a handwritten digit classifier. And lastly, a mobile API to run ML inference. Let's have a look at an example on how to call the MobileNet model from before. First, put the model anywhere in your app project folder, which allows you to require the model using a relative path. Second, create a React Native component to showcase your model. Third, add the PyTorch Live camera component with an capture callback. Fourth, call the model with the captured image from the camera. You can pass in values for variables defined earlier in the data processing specification. Last, get the top image class based on the model result and use it in your app logic. And that's it. We'd love to see what you all create. If you publish your apps, tweet with the hashtag PyTorch Live and we'll retweet some of them from the PyTorch Live account. And here's how you're getting involved with PyTorch Live. Visit the PyTorch Live website for tutorials and API documentation. Check out the PyTorch Live GitHub repository for the source code to make suggestions, report issues, and contribute pull requests. And join the Discord channel to connect with the community and start discussions. So, what's next for PyTorch Live? This is our initial approach at making it easier for you to build mobile apps and showcase your ML models to the community. It is also an opportunity to take this a step further by building a thriving community for ML researchers and mobile developers and share and utilize Pytorch mobile models and engage in conversations with each other. There are also short-term technical improvements that will be coming to Pytorch Live in the future. As mentioned earlier, we're working on a flexible data processing API to support custom data processing steps. The data processing API will be highly inspired by the Pytorch C++ and Python APIs, so you can transfer your learnings from previous uses of Pytorch. We will also be adding support for other ML domains that work with audio and video data. We hope you have a great time using Pytorch Live. Thanks for watching.
Hi, I'm Tao. I'm a software engineer on Pytorch mobile team. Today, I'm going to talk to you about the Pytorch mobile support for CoreML delegate. On-device machine learning can bring a range of benefits by moving computations to be local with data. It can improve privacy, ensure our feature work even without internet connectivity, and reduce latency. But on mobile devices, we are always power constrained, so it's critical that we perform computations as efficient as possible. Thankfully, modern devices have a range of specialist chips that can really help. GPUs, DSPs, and new ML dedicated hardware accelerators, also known as NPUs, can improve the power efficiency beyond utilizing the CPU alone. Each of these chips is suited to different tasks. Mobile devices can have different configurations of these chips. This complexity can make it hard for developers to best utilize the hardware. Pytorch Mobile provides a unified runtime for computation offload to different backends to improve developer efficiency and performance. On iOS, we support running models on GPU and CoreML. On Android, we support Vulkan and Android API. The Pytorch CoreML delegate was introduced in Pytorch 1.10. It can delegate model execution to CoreML framework at runtime on iOS devices. We provide an experimental interface to let you target Pytorch models to CoreML with the consistency Python API. You get the same familiar Pytorch APIs with no need to write Objective-C or Swift code. You can offload directly from CPU to dedicated hardware to get maximum performance out of your device. To get started, first download the Pytorch nightly build on your macOS machine. You also need to install CoreML tools. And finally, you'll be using the CoreML delegate API to optimize your Torchbench model to run on CoreML. Here is a code snippet of how to use the CoreML delegate on a pre-trained mobile Memoryview model. First, we download the model from Torchvision, and then we call torch.jit.trace to convert the model to a Torchbench model. Next, we use the to_backend API to target the model on CoreML backend. And finally, we save the model to a light interpreter compatible format. Note, we need to provide input and output shape information to do shape inference when converting the model. We can also specify the hardware you want to target on. By default, the model will run on CPU. In this example, we use all to allow CoreML to select the best processing unit to use, which includes the neural engine if it's available. When it comes to time for runtime inference, we provide nightly CocoaPods for you to try out. You can use the new model directly within your app. There are no code changes needed. Just switch your existing model with the new model. Real-time segmentation is a feature that can really benefit from the hardware acceleration. Imagine the case of trying to determine the foreground of the users from their background for a virtual green screen effect. You want to run this continuously at low latency to provide a responsive experience to users. But typically, you're also running a lot of computation in parallel at the same time. The Instagram team is now testing Pytorch CoreML delegate for their immersive 360 background feature. By offloading the computations from CPU to CoreML, they are seeing 80% latency reduction on iPhone 12 Pro or above devices, and 25% latency reduction on lower-end iPhones. The initial release supports a powerful but a small set of features. It supports for iOS 14 plus devices. It supports popular CV models from Torch Vision, such as MobileNet V2, ResNet, ShuffleNet, and SqueezeNet. In addition, we are hard working on the next set of features, including additional operator types, support for popular master class models, enable quantizations, allowing flexible input shapes. We are also investigating on supporting the new CoreML model format. So that was a brief overview of PyTorch Mobile support for CoreML Delegate. Download the PyTorch Mobile Nightly build and get started testing our demo app. Please do provide your feedback. For more on CoreML Delegate, check out our online tutorials. For more on PyTorch Mobile integration, please view our PyTorch iOS demo apps on GitHub. We can't wait to see how you take advantage of our full hardware capabilities with PyTorch Mobile in order to provide amazing machine learning experience on iOS. Thank you.
Welcome to PyTorch Developer Day. My name is Christian Keller, and I'm the product manager for the on-device AI platform and PyTorch Mobile at Meta AI. Today, Linbin Yu and myself will present the uses of PyTorch Mobile at Meta scale. Today, we'll address two topics. First, PyTorch Mobile in numbers at Meta, followed by a deep dive and a use case with real-time person segmentation. Let's take a look at some high-level numbers first. Our journey started in 2019 with the launch of PyTorch Mobile at Developer Day. In 2020, we expanded our offering from simply inferencing on CPU to providing additional inferencing solutions on GPU for iOS and Android. In 2020, we saw a major uptick in PyTorch Mobile usage internally. We have now reached meta scale for PyTorch Mobile usage and are excited to show you how far we've taken on-device AI. But first, what is on-device AI used for at Meta? Our usage covers a wide range of fields, from computer vision to language, speech, and ranking. The application domains also vary from augmented reality to integrity and commerce, to name a few. We have new teams showing interest in deploying AI on-device every day in new exciting fields. And now, let's look at how far we've taken some of these deployments. Where is PyTorch Mobile deployed? Today, we're in production on 15 surfaces on Android, iOS, Windows, macOS apps, including Facebook app, Instagram, and Messenger. We'll also deploy on creator apps like Spark AR and devices like Portal and Quest VR headsets. What is our reach? We have 1.4 billion monthly active devices deployed with PyTorch Mobile across those surfaces. These devices cover a wide range of hardware, going from high-end iOS and Android phones to older generation phones, delivering a consistent experience to our users across all of them. On those, we have 1.4 trillion inferences made monthly. To reach that scale, we have had to make PyTorch Mobile a reliable runtime, ready for scaling. These 1.4 trillion inferences power 45 billion individual product experiences, improving a wide range of products from video calling to creator tools and augmented reality. PyTorch Mobile is ready for your use cases, no matter the scale you're aiming for. These 1.4 trillion inferences power 45 billion individual product experiences, improving a wide range of products from video calling to creator tools and augmented reality. PyTorch Mobile is ready for your use cases, no matter the scale you're aiming for. Next, Linbin will talk about a specific use case, real-time person segmentation.
Hi, my name is Linbin Yu. I am a software engineer at Meta. Today, I'm going to talk about a PyTorch Mobile use case, which is real-time person segmentation used in Meta. Person segmentation model can detect if there is a person in the image, and if so, which pixel belongs to the person and which pixel belongs to the background. Then we can replace the background image with something else. Person segmentation has been used in many Meta apps, including Facebook, Messenger, Instagram, Instagram Reels, and AR Spark Studio. For example, person segmentation was used in virtual background for a video call. and background blurring, and in many Spark AR effects. Those Spark AR effects can either be developed by Meta or by third-party developers using Spark AR Studio. There are different models to do person segmentation, but to use it at meta scale, there are some challenges to overcome. The first one is latency. When we use person segmentation in a video chat or meeting, it must be real-time. That means the model must run very fast, ideally less than 20 milliseconds on most mobile phones. The second challenge is power consumption. When we use person segmentation in a video chat or in a meeting, it usually runs for a long time, like 30 minutes or even longer. If we don't control power consumption, the phone can easily be overheated or run out of battery. The third challenge is a unified experience on multiple platforms. The person segmentation model will be run on Android, iOS, macOS, and Windows, and the device can be very different. We want to use the same model to run everywhere, but the user experience must be the same. So how do we overcome these challenges? First, we develop a light-weighted model architecture based on FVNet v3, which is faster than the previous UNet-based model. And for low-end devices, we need to find a good trade-off between image quality and speed. So we generate a different model with lower resolution for these low-end devices. We also quantized the model. Quantization can greatly reduce the model size and latency. PyTorch Mobile supports 2 different quantization engines. For mobile devices, we can use QNPAC. For desktop, we can use FVGM. To reduce the power consumption, we can offload computation to GPU, NPU, or DSP on some devices using different PyTorch backend. PyTorch Mobile supports different backends, including Meadow, CoreML, Vulkan, and NAPI. This allows us to better utilize GPU, NPU, and DSP on these mobile devices. For person segmentation model, we can convert it to different backend and deploy it to different devices. For certain iOS devices, we use PyTorch Meadow backend to offload the computation to GPU. We are also testing a PyTorch CoreML backend to further reduce the power consumption and memory footprint. Similarly, for Android devices, we use PyTorch Vulkan backend to offload the computation to GPU. And we are testing Android NAPI backend to utilize DSP and NPU on certain devices. This is how we use person segmentation at Meta.
To get you started with PyTorch Mobile, you can go to our resources on our landing page in the pytorch.org website and ask us questions on the forums. Thank you for your time. We hope these examples demonstrated that PyTorch Mobile is ready to deploy at scale on your applications.
So hi everyone, my name is Alex. I'm a research scientist at Facebook AI, and along with Igor, a research engineer from my team, we're going to present Opacus, Differential Privacy for PyTorch. So first, I'm going to give a quick introduction to privacy in machine learning. Then, Igor is going to do a code demo of Opacus and present a performance benchmark of differentially private frameworks. Let's first do a high-level overview of privacy in machine learning. So, in recent years, AI researchers have trained larger and larger models, leading to improved accuracy by a large factor. These large models work great, but they also memorize a lot of information about the training set. In the case of language models, Carlini et al. Recently showed that it is possible to extract training data directly from the model. To do that, the authors make the model generate sentences and then filter them to find the sentences on which the model gives the best score. This is shown on the XKCD comic. Given some context, a language model will start to generate private information and thus reveal its training data. With their approach, Carlini et al. Are able to successfully recreate sentences from the training sets. This data extraction technique shows that machine learning models can be reverse engineered and thus reveal information about their training data. So how can we prevent that? The standard solution to this problem in machine learning is differential privacy. Roughly stated, differential privacy ensures that each data sample impacts the final model by less than some small quantity epsilon. Differential privacy enjoys nice properties such as robustness to side information, post-processing, and so on. In the next slide, we're going to see how we can make stochastic gradient descent, or SGD, differentially private. SGD iterates through all elements of the training set, grouped by batches. At each step, we compute the average gradient over the batch and use it to update the model. To make SGD differentially private, we need to change 4 things. First, we need to clip individual gradients to a maximum norm of C. Second, we need to add Gaussian noise to the resulting average gradient. But to do that, we need access to individual gradients, which is not efficient by default in PyTorch. So in Opacus, we implement an efficient version of this. Finally, we need to modify batch creation. Instead of randomly cycling through elements, at each step we flip a coin for each sample to decide if it goes into the batch or not. This is called a Poisson batch. Because of the post-processing property, we can not only do vanilla SGD, but also fancier optimizers such as Adagrad, Adam, etc.
Thanks, Alex. Hey, I'm Igor, a research engineer at Facebook AI. And now let's look at how we can apply differential privacy to your PyTorch training pipelines. When designing Opacus, we've followed 3 high-level principles. The first is simplicity. Opacus just does the right thing right out of the box. You don't need to know the details of the underlying differential privacy algorithms. You can just apply Opacus with simple 2-line code change, and that's it. The second is flexibility. We aim to support researchers that might do a novel research or explore new ideas. So Opacus is designed to be extensible and flexible, giving users ability to use custom code to support non-standard use cases. And on top of that, Opacus components are modular, so we can use different parts of the algorithm independently. And the third principle is performance. We know that with the naive implementation of the algorithms that we use, the training with DP can have a major impact on your training speed. We strive to minimize that impact and facilitate fast iteration on your experiments. In order to do that, we perform vectorized computations and, to better utilize GPU parallelism and also support distributed training. So now let's look at a code example and how to use Opacus for your model. We'll start with a normal PyTorch training script that the code's in gray. You initialize your model, optimizer, and data loader. And then you create a privacy engine object. That's the main entry point to Opacus. Then you call the make private methods from the privacy engine, passing model, optimizer, and the data loader to it. What it does is it adds some extra responsibilities to this PyTorch objects and returns them for you to use. And after that, you can just continue your training as you would normally would with vanilla PyTorch. There are 2 required parameters that you need to pass to privacy engine. First is noise multiplier, determining how much noise to add and therefore how private the model is. And the second is max grad norm, how aggressive you want the gradient clipping to be. Let's now unpack what happens when we call to make private. As Alex explains in his part of the talk, there are 4 components of DPSGD: computing per-sepal gradients, gradient clipping, adding noise, and uniform batch sampling. In the make private methods, Privacy Engine assigns each of those responsibilities, each of those tasks to relevant PyTorch objects, and returns a wrapper that does everything that the original object do, but also with added responsibilities for DPSGD. For example, the wrapped model would behave just like the original PyTorch module, but would also calculate per-sepal gradients for its parameters. In a similar fashion, Optimizer would do gradient clipping and add noise, and the data loader would flip to use Poisson sampling. Now let's talk about privacy parameters. The main one we want to focus on is epsilon. That's essentially the privacy budget. It depends on the noise multiplier and the number of training steps that you take. Apacus keeps track of all of those parameters and lets you determine how much privacy you've spent up to a given point by calling the method called getPrivacySpent. In some situations, you might face external requirements on epsilon. For example, one of your requirements for an app could have a fixed privacy budget. In this case, Apacus lets you invert the computation and instead of noise multiplier, pass down the target epsilon, and it will determine the necessary noise multiplier for you so that by the end of the training, you would get the expected privacy budget. Circling back to the efficiency, let's take a look at distributed data parallel. Well, there is not actually a lot to look at. If you have a DDP training pipeline already, the only thing you need to replace is replace vanilla distributed data parallel wrapper with differential private DDP wrapper before passing it down to the privacy engine. And since we've started talking about efficiency, let's take a look at some numbers. A team at University of Waterloo released a paper comparing different DP-SGD frameworks on a simple set of benchmarks, linear model on MNIST, convnet on CFAR, and embeddings and LSTMs. And as you can see, Apacus is best in class in terms of performance compared to other privacy frameworks on PyTorch and TensorFlow, for example, Privacy or TensorFlow Privacy. And even compared to JAX, which is a framework with built-in capabilities to efficiently compute per-sepal gradients, and that's, by the way, the part responsible for the biggest hit on training speed, Apacus demonstrates comparable performance on larger batch sizes. Before we wrap up, I'd like to share some resources you can use to learn more about Apacus. First, we have a website called apacus.ai with a great set of tutorials on Apacus and DPSGD. Apacus is open source, so feel free to head to our GitHub, open an issue, or send a pull request. We welcome and really appreciate external contributions. And finally, we've recently published a paper with a detailed description of Apacus design and implementation, and you can find that on arXiv. And with that, thank you so much for coming over to this talk.
Hi, my name is Narina Kokhlikian. I'm a research scientist at Meta. This presentation is about model interpretability with CAPTM. In this talk, we will cover topics on model interpretability beyond feature attribution and feature importance. In the first part of the talk, we will focus on adversarial attacks and input perturbations. And in the second part of the talk, we'll dive deeper into concept-based model interpretability and recap the talk with future directions. First, let's define what model interpretability is and what it means interpretability beyond feature attribution. As you might remember from our previous talks, model interpretability is an area of AI research that helps us to debug our models and understand how those models arrive to certain decisions. This way, we can gain more transparency about the inner workings of our models and can potentially control their behavior certain ways if necessary. During PyTorch Developer Day 2020, we talked about CAPTM library and focused on feature attribution methods and their evaluation metrics. We expanded CAPTM beyond attribution and added support for robustness and concept-based model interpretability, which can be used in conjunction to enable deeper analysis with diverse interpretability tools. This form of new unifies a key area of CAPTM aside from multimodal and ease-of-use aspects of it. Let's look into adversarial attacks, input perturbations, robustness metrics, and how they can be applied to real models using Captum library. Adversarial attacks help us to fool ML models by adding human imperceptible noise to inputs. In this example, we use FGSM white box attacks to add slight perturbation to the input. The image looks semantically almost the same before and after the perturbation to human eye. However, the model doesn't see that and misclassifies the image as a warthog. In this example, we show how to use FGSM algorithm from Captum library. To use FGSM, we import it from captum.robust package, create an instance of it, and pass our model, which in this case is a ResNet model, and other necessary arguments such as lower and upper bound for input data. We then call perturb on the FGSM instance by passing our input, which is the trained image, and other parameters. This will return us a minimally perturbed input that was misclassified by the ResNet model. We can then visualize this side by side with the original image. As we can see, perturbed image is semantically unchanged, and it will still be seen as a trained to human eye, but the model prediction has drastically changed for perturbed image. The model classifies it now as a plow. Note that we can also use the perturbations not only to generate adversarial examples, but also counterfactuals. In this example, we use minimum param perturbation method to generate counterfactual examples. More specifically, we would like to know how much should we change our input image of a train so that it gets misclassified as suit. Knowing that the index of suit class is 834, we can define such a criteria in an auxiliary function that will be used from the algorithm in order to decide if the model changed prediction label to suit. We can then pass that function to the constructor of min param perturbation along with the model attack function, which performs pixel dropout or ablation in this case and other required arguments. Similar to FGSM, we can then compute perturbed image by calling evaluate and then visualize side by side. Here we can see that most of the parts of the train and background are dropped, ablated, except the suit on the person running to catch the train. This shows that after ablating train context and the background in the image, the classifier starts focusing more on the human suit on the image. Now let's look how we can compare different input perturbation techniques and adversarial attacks side by side. To do so, we need to import Captum attack comparator, create an instance of it by passing our model and the list of comparison metrics such as accuracy or logit. As next, we define a list of input perturbation techniques such as image rotation, Gaussian blur, or any type of adversarial attacks such as FGSM, or we could choose PGD or other attacks that we are familiar with. We then call evaluate by passing our input image and the ground truth label. Evaluate returns statistics about the accuracy and the logits of the model, which in this case is visualized in a spreadsheet. As we can see from the spreadsheet, the random rotation and FGSM drop model accuracy from 100% to 19% and 0% accordingly, while Gaussian blur transformation left the model prediction unchanged. Now let's look into another area of Captum library called concept-based model interpretability. Concept-based model interpretability aims to explain model predictions in terms of abstract predefined concepts. Here we have examples of such concepts. For images, stripes and random images, and for text, it could be, let's say, positive adjectives and neutral terms. We would like to understand how important are those concepts for model prediction. In this case, we have sentiment analysis classification model that has two convolutional layers, conv1 and conv2, and we would like to know whether positive adjectives contribute to model prediction when making predictions using movie rating dataset, as also visualized on this slide. There is a well-known method called testing with concept activation vectors, TCAV, which helps us to quantify concept sensitivity to model predictions with respect to a specific layer in our model. In this case, we will consider convolution layer 1 and layer 2. In order to use TCAV from Captum library, we need to define the concepts first. In this case, we define them using concept class, which requires user predefined data loaders, which will help us to load concept examples batchwise. The goal of TCAV is to learn a hyperplane that separates concepts from each other. In this case, we'll learn a classifier that separates positive adjectives class from neutral terms class for any given layer L. The vector that is orthogonal to the separation hyperplane and points towards a specific concept class is called the concept activation vector, or CAV of that concept. In this case, we visualize CAV vector for positive adjectives. We can then take any text example, in this case movie rating review, as inputs and measure model sensitivity to our positive adjectives concept when making prediction for the inputs. To do so, we would need to compute the attribution of our input prediction with respect to selected layer L, for which we already computed the CAVs. And then we will compute the dot products between the attribution and CAV vectors. This gives us an important score of concepts when making predictions on inputs for a given layer L. This arithmetic operation happens under the hood in Captum when we use TCAV class by passing the model, in this case it's our sentiment analysis model, and a list of layers for which we would like to compute the TCAV score. When we call interpret on the instance of a TCAV class by passing inputs and a list of concepts, it computes TCAV score for each layer specified in the arguments of a TCAV class for all concepts in the interpret method. We can then visualize the TCAV score using a bar chart for each layer. In this case, we visualize TCAV scores for both convolutional layer 1 and layer 2 for both neutral and positive adjectives concepts. We can see that the importance of positive adjectives is close to 1, and for neutral concepts is close to 0. This is what we expect because we use positive movie rating samples to make predictions. We plan to expand Captum beyond the areas that I mentioned and add support for influential instances, model comparison, and similarity metrics. So to recap, I started talking about the attribution methods and how we expanded Captum beyond those methods, adding support for concept-based model interpretability and robustness metrics, attacks, and input perturbations that can help us to generate counterfactuals. We would like to invite you to try out our library and provide your feedback in forums or GitHub. And we are excited to explore new directions with respect to influential instances and model comparison and similarity metrics. Thank you.
Hello everyone, and welcome to this talk, which is an introduction to remote data science. My name is Andrew Drask, and in the next few minutes we're going to be walking through three main steps. So first we're going to talk about motivations for remote data science. So first is going to be some motivation for remote data science. We're going to see a little bit about how it works, and we're going to finish by talking about a new opportunity for you to learn more about this exciting technology. So first, let's talk a little about the motivations. First setup for this is really about how our ability in society to answer important questions is limited by the amount of data that we have access to, because that data simply is not at our disposal. It's in another country or another department. And this leads us to kind of the core premise of this talk, which is that solutions to really important problems already exist, but we just can't access those solutions because we can't access the training data and the machine learning data that we need to be able to solve them. So there's a wide variety of examples that are like this, but we're going to drill down into just a couple. So first one we're going to talk about is breast cancer. Unfortunately, around 1 in 8 women encounter breast cancer at some point in their lives around the world. And this leads to as much as 700,000 deaths per year from breast cancer. And one of the main contributing factors to this death rate is that we have a really difficult time detecting it, meaning when you go in for a mammogram and a radiologist takes a look at the scan, many places have as high as a 1 in 4 false negative rate, meaning that 1 in 4 women who go in who have cancer are told that they have a clean bill of health. Then they wait 2 more years before they have another scan, and the cancer is really advanced by the time they find out about it. Breast cancer classification should be a relatively straightforward image classification problem, which deep learning and machine learning is really good at. But unfortunately, machine learning models, even the best ones that are put into production, are even worse than typical human-based screening programs, with a 1 in 3 false positive and false negative rate being common. And this is because, this is my opinion, that the largest data set that we have to work with is only 3 million images. And in deep learning and machine learning communities, we know that this is not a very large data set. And this is despite the fact that around 8 billion images have been produced in the last 10 years alone. So we have this huge latent resource of images to work with, but we're only working with tiny slices of it. And as a result, machine learning models are not actually solving this problem, despite the fact that they probably could. So this brings us back to our general theme of how solutions exist to important problems, but access to data for those solutions is limited. And I want to talk about one more use case real quick before we talk about the actual technology. This use case comes from the United Nations Privacy Enhancing Technology Lab, or the PET Lab, which is a new body that is piloting a lot of the technologies that you're going to talk about today. Specifically, they're looking at a trade-related use case. So you may or may not be familiar, but Canada and the United States, for example, each measure the amount of goods that are going over the Canadian-US border. But often these things don't match. So usually they match just like they do here, but sometimes goods can disappear, right? Where Canada has record of goods that are supposedly going to the United States, but the United States doesn't have any record of having received them. It turns out this is a really important thing for nations to be able to measure, and so the new UN PET Lab project is working with 5 different UN member nations to be able to collaborate together on their shared data resources to understand how goods are flowing without having to centralize those data assets into one location, right? And again, this is all just about this same core premise where there are solutions to really important problems that already exist, right? In theory, but access to the data necessary for those solutions is too limited for us to accomplish them. Now, in this talk so far, you might be wondering, why not just centralize the data? Why not just put all the data in one place that you need for, say, breast cancer or monitoring global trade to solve these really important problems? And there's a host of different reasons that we could consider why this might be the case. But I want to focus on one that is simply too inconvenient. And just anecdotally, if you wanted to solve this breast cancer classification problem that I mentioned, and you were going to acquire data from 1,000 different hospitals, that's 1,000 different institutions that you have to get on the phone with, that you have to talk to their legal department, they have to talk to your legal department, you have to go back and forth, and you have to manage the risk, and they're going to ask where you're going to put the data, and who are you, things like background checks, and it's just such an enormously complex and time-consuming challenge that it's just intractable. Even if you have lots of money and willpower, no one has overcome this challenge thus far. And this reminds me of how sort of public data used to be, in the sense of, before the internet, if you wanted to know about a business or prices, or you wanted to order airline tickets, you had to get on the phone, right? You had to actually call a business and talk to a real person and ask them. And today, the private data industry is still a lot like that. And what we're going to be talking about in the next few minutes is really the same solution to kind of the same problem, which is we should be able to take private data, put it into a server, and other people should be able to answer questions using that data without us having to be involved as data owners at all. Inversely, as a data scientist, I should be able to just access the ability to answer questions using important data in the same level of ease that I currently access the internet. So this is the field of remote data science. And this is really what remote data science is all about. So you have an organization that has data, you have a data scientist who wants to be able to work with it, and they remotely access this server to answer their question instead of downloading the data set itself. And this isn't all about data scientists accessing individual institutions. This is actually about data scientists accessing a whole internet of data that is sensitive and private, that they never actually obtain a copy of, but they can still use to answer important questions. So in the next few minutes, now I want to transition to how this technology actually works. And this is going to be a very short sample of what this technology is actually like. And if you sort of like what you see and want to learn more, then you can check out the educational resources that we'll talk about at the end of this talk. So this is going to come from a library called PySift. And PySift allows you to sort of have the additional functionality in partnership with tools like PyTorch to be able to study data that's located at different machines. So let's start at the top with a simple experiment where we're going to locate data and do a little data science project. So I import Sift. First thing I need to do is source a network. So a network is just a registry of where private data assets exist. Think of it like sort of Google search, but for private data instead of public. So I take a registry, I connect to that registry, and inside of that registry are what's called domains. So domains, much like a website domain, are just different servers that exist on the internet that are holding private data, right? So let's say I choose 2 of these domains, and now I get a variable, so we'll say Canada and the United States, that allows me to talk to those domains, right, and to be able to interact with them. So I connect to both of these domains, and this brings us to sort of the analysis. So now I've got access to data in Canada, and I've got access to data in the United States, right? So 2 different locations. So the first thing I need to do is figure out what my privacy budget is. And the privacy budget is the limitation on the amount of information that I'm going to be able to pull out of these servers automatically. So it looks like I've got 200 epsilon of privacy budget from Canada, and I've got 200 epsilon of privacy budget from the United States sort of to work with, right? And if I run out of privacy budget, I can't pull any more data out. I can't pull any more sort of information out. That's sort of what keeps the data safe. So I'm going to select a couple data sets. So see how the data sets would allow me to list them. I'm going to select number 32. Looks like we've got the amount of imports and exports of dairy that the United States knows about to Canada, and Canada to the United States. Inversely, we have the same going the other direction. And now that I've got these 2 data sets, or I've got pointers to these 2 data sets, variables that are pointing to data in 2 different countries, right? Now I'm going to do an analytic. So I've got this pointer on the left, USA exports to Canada. I've got the pointer on the right, Canada imports from USA. These are each pointing to tensors that are in different servers on different parts of the world. It should be impossible for me to subtract them by each other, right? The data is on 2 different machines. But what happens right here behind the scenes is it just secure MPC shares using an input privacy technique called secure multi-party computation. And this returns to me a pointer to these encrypted shares at both locations, right? This means that I perform this subtraction, but no data has actually left either institution. Instead, an encrypted protocol was used to be able to actually calculate the result and maintain the result in an encrypted state with shares at each of these locations. And finally, in order for me to download the result, what I need to do is add some differential privacy noise to the result so that the automatic privacy budgeting accounting mechanism goes, so you had 200 privacy budget left, so you just add this amount of noise. Looks like I can let you download this result, right? And I even have a little bit of privacy budget left over. And what I hope you see in this sort of end-to-end flow is that sort of in the span of 1 notebook, I can go out on the internet, look for some data, find some data, perform computation against that data, even if it's data located on different machines, and then download my result without having to get on the phone with anybody, without having to do data partnerships, and most importantly, without having to actually download a copy of the data set. And if you'd like to learn more about this, I'm super excited to announce that with the generous support of PyTorch, the OpenMind community is releasing today a brand new course teaching you how to participate with these types of technologies, both how to deploy data into a server and advertise it on these types of networks, as well as how to participate as a data scientist. And this will all prepare you for a forthcoming United Nations certification on remote data science. So check out these courses. Please go to courses.openmind.org, where you can register for free, just like 8,000 other people already have. Thank you so much for your time and attention, and I hope you have a great PyTorch Dev Day.
I wanted to first thank our keynote speakers, Dougal McLaurin and Philip Tilley, on giving fantastic ideas to us and giving fantastic software to us that powers the future direction of the community. And in some sense, I'm deeply thankful to them for doing work that is not always appreciated in all contexts. They're building out and exploring ideas that will eventually, maybe someday, come into a mainstream framework like PyTorch. And when you use that feature, you're going to be like, wow, like this is so cool. How did PyTorch come up with this? But I think some of the fundamental credit really goes to people exploring these ideas and helping us set the direction for the future. And to that, I'm thankful to Dougal and Philippe earlier today, but also to other projects within the PyTorch community and the larger ML ecosystem. I want to thank the Julia developers. I want to thank, more specifically, the Flux developers in the Julia community. And I want to thank the JAX developers and the many other exploration projects that have happened, the deep speed people, everyone who has been involved in building out cool, exploratory, idea-driven projects within the ML framework space. I really thank all of you because you're just pushing the field forward, and I think you're not appreciated enough for it.
Doing here. I would like to take next couple of minutes to thank those who have contributed to this event, as well as what to expect the rest of the event. I've been working on PyTorch marketing for about the last 3 years. And every day I feel really lucky and fortunate to work with community members who are smart, but also humbling and caring for others. And I think that's what makes PyTorch community different from other communities that I have worked with in the past. And just like the event today, there are a lot of talks and posters that are contributed by our community members. I know your time is super valuable and busy, but thank you for working with us and sharing with the community. All right, to talk about what to expect tomorrow. So tomorrow is our networking and poster session. Please note that session for tomorrow require registration. So if you're registered users, you will be able to see your login information in your email or on our event website. And we want to make sure that this event is knowledgeable, cultivating for our community. So make sure that you keep those login information to yourself, because this event is for those who have contributed to PyTorch or use PyTorch in a meaningful way, for you to have very cultivating conversation together. At 10 a.m. Pacific time tomorrow, there also will be a community talks for about an hour. These community talks will be available through gather.town, as well as our YouTube channel. And last but not the least, I want to talk about the fireside chat that is coming up. So fireside chat will start at 12:30 p.m. Pacific time. So fireside chat will be between Sumit Chintala, who is co-creator of PyTorch, and Jan LeCun, who's a vice president of Meta AI. The fireside chat will have very interesting conversations, such as what are they most excited about in AI? Or where do they think the future of framework is? So it'll be very thought-provoking as well as interesting discussions. So I hope to see you there. Session will start at 12:30 p.m. Pacific time. So make sure you set a reminder, and make sure I want to make sure that I can see you there. And for those who are thinking like, hey, I actually need to go to bed, or you're sleeping, don't worry about it. All these videos will be available through our YouTube channel. So you can go to youtube.com/PyTorch, and you'll be able to see all the talks next few days. Thank you for joining us today, and excited to see you today and tomorrow. And hopefully we can see each other in person. Thank you.
I'm Samit Chintala. I'm here at the PyTorch Dev Day with a very special guest. I've been working in the PyTorch community for the last 5 years, helped start and fund the project. And today with us, there's a very special guest who is no other than Jan LeCun. Jan, I've known him for over a decade. He has been my mentor. Jan LeCun has been one of the pioneers of deep learning who has started this whole new cycle of AI, and he has won a Turing Award for it, the highest award given in computer science. And on top of that, Jan LeCun is the chief scientist of Facebook and a professor at NYU. Just to step back a little bit, that's not what I'm really excited about to introduce Jan here today. Jan built a bunch of frameworks in the 80s and in the 90s that actually are the foundations for a lot of ideas in PyTorch. So the frameworks he built, Lush and SN, that I know of, and I'm sure he'll talk about more of that stuff, that they have been like fundamental in shaping our ideas. And like if you're using PyTorch today, you're sitting on, you're using on some of the ideas that Jan has come up with. So with that, I want to just quickly check, Jan, do you have anything else you want to add on a personal note?
It's a wonderful introduction. I don't have anything to add, other than the fact that some functions in PyTorch have the same name as the stuff that I wrote back in 1991.
Nice, very cool.
My interest in writing deep learning frameworks, as we call them today, goes back to 1983. Wow. Which is when I wrote the first one. It was called HLM, actually, and it could do backprop and various other things. But then I realized that I could not really control it very well. It had a very simple command language. It was written in Pascal. And it had a simple command language. And I realized, I need to have loops, and I need to have functions, and I need to basically have a programming language. So I started, studying what front-end programming language could I use for my next generation neural net simulator. And I almost settled on Forth, okay, but eventually settled on Lisp.
Nice.
Because it's easy to write your own Lisp interpreter. We're talking about 1987, and there was no Python, there was no MATLAB, there was no language you can just download off the internet. There was no internet. And use as a front-end language, you basically had to write your own. So I got together with Léon Bottou, who is at Facebook, and we wrote a Lisp interpreter and then hooked up a sort of numerical library for kind of neural nets, very specialized for neural nets in the back. Then I moved to Toronto, and I kind of finished it, and Léon, on his side, kind of kept working on it. So that was called SN, for Simulateur Neuronal. This was kind of the French word, the French name. And then Léon had this idea in 1991, roughly, that the right way to build a neural net or deep learning system, it wasn't called deep learning then, was to basically have functional modules that you assemble in graphs, and then you get this kind of automatic differentiation. They don't have to be neurons and weights and stuff like that, right? And I started implementing that, and he implemented the back end. So this was in the early 90s. And that kind of ended up with help from Patrice Simard and various other people in a system called SN2, which eventually we open sourced in the early 2000s under the name Lush.
Nice.
And a lot of people kind of, that was sort of the inspiration behind Torch.
Yeah.
The first Torch, which had a Lua language as the front end, for Café 2, or for Café 1, actually, and Café 2 within Facebook, and then later TensorFlow and PyTorch. So, they all use this model of you assemble blocks and you kind of differentiate automatically.
Nice. So a couple of nerdy questions before we move on. So HLN and SN, at least HLN, I presume, was not floating point, or was it?
It was floating point, but very slow, because at the time the machines couldn't do that very much. So it had a mode where you could turn on fixed point, because that was much faster.
And did you guys usually train in fixed point or floating point?
We were, whenever we were experimenting, it was floating point. Like even the first version of SN had you could switch the mode from floating point to fixed point. And because you have to realize, Leo and I developed the first version of SN on a Commodore Amiga. Okay, we both have Amigas, and those things had a 68,000 processor, but no floating point accelerator. So floating point was really slow. So we had a fixed point mode. And then, we ended up having Sun workstations and stuff like that were floating points. So it was.
And did you guys have any accelerators you use, like DSPs or any other accelerators?
So that came a little later. So I joined Bell Labs in 1988, and started experimenting with convolutional nets and things like that. And then we wanted to build. After the first results of convolutional nets to do character recognition, we wanted to build a demo so we could show to the engineering groups and the product groups and stuff like that at AT&T. And so with a few engineers in the group, I wrote basically what amounts to a compiler that would take the convnet, prune it, suppress the small weights, and then basically generate a self-contained piece of C code that we could compile on a DSP board.
Nice.
Because at the time, the PCs were incredibly non-powerful. We're talking 1991, roughly.
Not even mainstream GPUs.
No GPUs, and even the GPUs were slow. So it turns out AT&T was building a DSP chip, and I was selling a board with a C compiler, and that DSP was capable of 20 megaflops, which was completely amazing at the time.
That is.
You could even get that in a workstation.
Yeah.
You were getting maybe 2 or 3 megaflops in a workstation, but certainly not 20. So we would put this in a PC, and then we had this demo. There's a video on YouTube where you see me put my list of numbers under a camera and hitting a key, and that's running on the DSP, and it had a compiler and something that kind of makes the computation cheap enough.
Very cool. So we've gone through a ton of breakthroughs and research in the last 2-3 decades, mostly in the last decade. So I'm sure you've seen it all. You've seen a lot of things go on. What's top of your mind right now?
Well, so it's no secret that I'm sort of a big supporter of this whole idea of self-supervised learning. And I see this as one of the 2 or 3 main problems that are kind of, that we need to go beyond if we want to make true progress towards kind of more intelligent systems, right? So one is allowing machines to learn like humans and animals. Currently, the type of learning paradigms that we use are really not nearly as efficient as what we can observe in humans and animals. So that's one problem that we need to solve. Second problem we need to solve is allowing machines to reason in ways that are compatible with deep learning and gradient-based learning more generally. And so, for tasks that they're not like perception where, you show an image, you get an answer. But tasks where you need to plan, you need to reason.
Yeah.
And it's not entirely clear how to do that. And there's big conceptual battles about what the best approaches are for that. Yoshua Bengio is interested in that as well. And, there's a lot of work at Facebook and various other places on how you do this. And then there is a third problem, which I think is not being really addressed at all, which is that with the type of deep learning that we have today, we can train machines to represent the perceptual world, but we don't have any ways to train them to represent the world of actions, or the world of action plans, I should say, right? So, you want to get from here to San Francisco, you know that you have to go to the airport, blah, blah, blah.
Right.
You're going to decompose this task into subtasks, right? And all the type of tokens that you use for those subtasks are things that you learned. They're not things that you were born with, right?
Yeah.
How do we get machines to learn those representations for action plans?
Right.
So that's the third problem, I think. But this one is kind of some way down the road.
Yeah.
The first one really we have to solve is how do we get machines to learn how the world works? How do we get them to learn, accumulate a lot of background knowledge about how the world works through observation, training them to represent the world, so that whenever a particular task shows up, we don't need to train them with millions of examples. We can, like a small child, you show the small child a couple photos of or drawings of an elephant, and
yeah, that makes sense. So, a couple of clarifying questions here. So for the second and third task, like I think they're somewhat related to each other. Like, are you? So there's a general. This area obviously has gotten a lot of interest. So people are talking about, should we use deep learning for the first part, like the perceptual stuff, and then use symbolic AI, like classical, like the COQ, or like various languages and projects from back then. I think like AI has seen a phase of symbolic AI being at its peak with fuzzy language and stuff like that, right?
Right.
So are you saying there would be a hybrid, or are you saying there would be just learning methods with the right representations that would just do all of the like discrete planning and stuff like that?
So I think it's entirely possible that there will be systems, perhaps in the short to medium term, that will combine deep learning, sort of pure deep learning things with kind of more classical, good old-fashioned AI, if you want, or symbol manipulation. But there is a lot of evidence that even deep learning systems can do symbol manipulation in some way, without necessarily being explicitly driven to do so, in a sense that we don't have to hardwire the symbols into the system. So there's this experiments that were done by our colleagues on, can I do symbolic integration of a differential equation using a transformer, train a transformer to do this, and you can, and it works, which is pretty incredible. So I think ultimately the solution I would prefer is one in which the reasoning part is done with not with symbols, but with vectors, essentially, right? Patterns of activities and whatever. And this is not, my idea or anything. Jeff Hinton has been advocating for things like this for 40 years. So not a new concept. The question is, how really do you do it? How do you make reasoning compatible with deep learning, essentially, with gradient-based learning, whether it's deep or not?
That gives a lot of interesting perspective into how you're thinking about, I think, your priorities on like what we need to make progress in AI. Did you have any thoughts on all the fundamental stuff that's already been broken through within the context of machine learning and AI, and the applications of it? Like, not just the like more fundamental, how do we get to superhuman intelligence, but how do we exploit what we already do well? Do you have any general thoughts on that?
Well, so the amount of stuff we could apply, the current techniques that we already have is mind-boggling, right? I mean, there's just not enough people who are trained to do this right now to kind of really do a good job at it. But so I think over the next 10 years or so, we're going to see a dissemination of deep learning AI technology in all corners of the economy, and at least that's what the economists are telling us. And perhaps have a measurable effect on productivity and economic growth and things like that. But I'm more interested in what's happening upstream, right? So there's a lot of really interesting concepts that people have come up with over the last few years that I found sort of have a lot of potential to kind of change the way we do things. So things like graph neural nets, for example, and graph convolutional nets, and invariant, equivariant neural nets, and there are libraries in PyTorch, right, to do graph neural nets, some of which come out of my lab at NYU actually, and there are things like reversible models. So people are trying to sort of learn densities in high-dimensional spaces, and for that you need to have functions that you can invert for various reasons. Generative models, obviously, and then self-supervised learning we were just talking about. There's a bit of a debate, or not a debate, but like a lot of interesting things happening in self-supervised learning. It used to be that self-supervised learning was, it didn't used to be, but there are situations where in self-supervised learning, what the main paradigm is basically an autoencoder, right? You give an input, maybe it's corrupted a little bit, and you run it through a big neural net, and you train the neural net to recover the sort of clean version of it. That's called a denoising autoencoder, right? And that's what all the NLP systems use, the BERT style, Roberta, etc., right? And that's created a revolution in NLP. There's no question about it. This doesn't quite work just like that. You can't transpose this to the realm of images.
Yeah.
And the reason is because if you want to reconstruct an image, you have to deal with the fact that there are many, many different ways to reconstruct an image. In text, it's easy to handle the fact that there are multiple words that could be present at a place where you mask the word, and you can represent a distribution over all words, but we don't know how to represent distributions over images.
Yeah.
And so those things don't work. So the thing that actually works is what's called joint embedding methods, which draws on stuff that I worked on in the early 90s, and Jeff Hinton also worked on, called joint embedding architectures, a special case of which is Siamese networks. So
right, Dr.
basically,
Lim and stuff.
Dr. Lim and various other algorithms of this type, where you have two neural nets that may or may not be identical, and you show it two different versions of the same image, and then you train the outputs to basically be the same.
Right.
And then you have some ways of making sure that when you show two images that are different, the outputs are different, and that's where things are hard.
Yeah.
For that, there are contrastive method and non-contrastive method. I'm really excited about a set of non-contrastive methods that people have come up with over the last year. So that is very exciting to me.
Nice.
Probably more exciting than a lot of stuff in the last 10 years, actually.
Yeah. I want to talk a little bit sort of on the related subject, but actually very different. What do you think about the future of current machine learning frameworks? Where are they going to go?
I have very peculiar ideas about this. So first of all, I have to tell you about my own taste, right? My favorite programming language is Lisp. And for me, Python is an abomination. But of course, I know that Python is what people want because it's convenient, it's there's tons of libraries, there's already a lot of code, it's kind of easy to interface and everything. So Python is what people want.
Yeah.
Now, if you want to use Python as a front-end language for a numerical library, it's probably the worst possible choice, right? Because it's slow, it's not compatible, you can't type, the objects and things like that. And so it's horrible. But that's what people want, and you have to take that into account. So what's happening right now in the PyTorch framework and ecosystem and other places is that people are kind of trying to sort of inch their way, towards kind of compiling more and more of the Python code, which I think is great, right? So there's all those efforts for there's the JIT, of course, in PyTorch. There's other attempts to do things like a functional version of PyTorch that looks a bit like JAX, where you can just write your function. That looks a little more like Lisp, actually. Things of that type that basically kind of fix the main limitations of Python. The other issue with Python is for productization, right? You want to have a self-contained piece of code without having to drag the entire Python runtime with you. And so, how do you detach your system, which most of the time is not just a neural net, right? There's a bunch of code around it. So that again sort of raises the question of, is there going to be a future where either we sort of ease the community into something that looks like Python but basically is compatible and more compact and everything, or kind of a sort of two-language type ecosystem where the low level would be in kind of a domain-specific language that you can intersperse with Python code. So you were working with me at NYU, and you remember Lush, and Lush had this possibility: you would write Lisp code, and then you would do hash brace, and then you could write C code and refer to Lisp variables, and that was wonderful, right? Because you could intermix code any way you want. So that's kind of one of the directions that I see people going into.
Yeah.
And this may be sufficient.
Yeah.
We'll see.
What advice would you give to them on whether, let's say, they want to be a scientist or an engineer, separately, or maybe a hybrid of both? What would be your top things that they should go do?
Well, so yeah, it depends a lot on the type of career you want to have. But what I would my advice, which I've been giving for years in various contexts, is learn things that are difficult to learn when you're young and impossible to learn when you're less young. Okay, so these are things like physics and math, basically, right? You have to learn that stuff when you're young. And why am I saying you should learn physics? Like, why should you take a course? Like, if you had a choice between taking a course on, I don't know, mobile device development, software development, or quantum mechanics, take quantum mechanics. Why am I saying this? Why is quantum mechanics relevant to machine learning? Turns out it's the same math, or statistical physics. It's the same math that you use for understanding deep learning systems, the dynamics of learning in high-dimensional spaces, those models I was mentioning earlier, invertible models, those are based on quantum physics, basically, unitary matrices and things like that. And there's going to be more and more uses of machine learning in the sciences, if you are interested in the sciences and research. So if you want to become a scientist, even a physicist, a chemist, a biologist, deep learning is going to be one of the main tools that is going to be able to take us forward. And if you have a sort of double expertise of knowing about machine learning and deep learning, but at the same time being a physicist, a chemist, or a biologist, or an economist for that matter, or just about anything, you're going to have a combination of skills that doesn't exist anywhere, and that makes you valuable, that makes you unique.
Yeah.
Try to make yourself unique. Now, the other reason I say, take courses on quantum mechanics and linear algebra and probability theory is that this is knowledge that has a long shelf life that will kind of learn you to, teach you to reason about certain things that otherwise you wouldn't have no idea about. Whereas if you learn a piece of technology that appeared in the last 2 years, it may disappear in the next 2 years. The model may be completely different, right? So, learn things that have a long shelf life. Then if you want to make yourself known or remarked, just, participate in an open source project. That's the best way. We didn't used to have that, right?
Right.
But now you can, you can contribute to an open source project, and your name is on the Git, and you can claim that, and get some credit for it, and it will kind of help you get noticed.
That makes sense. That's how I got my first and second jobs. So definitely would recommend that advice. I just wanted to close out on first, I want to thank you for taking the time to speak with us today. And do you have any other closing thoughts you wanted to talk to the community about anything else? Could be pretty much, the floor is yours.
I think there's going to be another revolution of AI over the next few years, probably due to the combination of things like self-supervised learning and things like that. If that revolution occurs within the next 5 years, I think we're lucky. It might take longer, and the question is whether it's going to take more time or longer than the patience of the people funding the research, who may get impatient, right? So we need to have household robots. We need to have machines with common sense, because in a few years or decades, we're all gonna wear, augmented reality glasses, and we're gonna talk to our virtual assistant, who is gonna mediate our interaction with the digital world, is going to, help us deal with the flow of information that we are bombarded with, on a continuous basis. And for that, we need machines that can, dialogue with us, that understand us, that have some level of common sense, understand how the world works, everything, all of that. And then, so those are the two big applications. Robotics, household robots, a robot that is as agile in terms of its mind, maybe not the mechanics, as a house cat. We don't have that. We're nowhere close to that.
Yeah.
And on the other side, on more of the reasoning and sort of human type intelligence, have sort of quasi-human level intelligence virtual assistants that we can talk to, because we're not going to get our phone out of our pocket anymore, right?
Right.
We're going to have a virtual assistant that we can talk to through our augmented reality glasses, and so that's going to be a very different world, and we're going to live part of our life in the metaverse, right? So, metaverse is going to be populated by AI agents. In addition to human, to sort of, to people. So a lot of possibilities there.
Very cool.
So Sumit, I know, I want to ask you a question. I know at Facebook you're working on robotics and things like this, there's a little bit of tinkering there, but do you have any sort of personal projects or personal interests that you might want to tell us about?
Personal projects. Well, I think this is very hard because to me, I have this philosophy that I only work on whatever is fun. If I don't feel like it's fun, then I don't work on it. So to me, work and personal aren't that far away from each other. The robotics thing you bring up actually started as a personal project. I was like, I need to build a robot to, I hate doing dishes and like loading up the laundry. Like, why in 2021 are humans still doing this stuff? Why can't something else do it for us? That's kind of how it started. And then I got into it enough that I kind of spend a lot of time on it these days, doing home robotics and stuff.
Right.
Yeah. What about you? Let me ask you. You have, I think, just knowing you for enough years, you have so many nerdy personal projects that are super cool. I'd love to hear some of that stuff.
I mean, there's stuff I like to do which are projects or not. So, I'm into sailing, I'm into astrophotography. And in fact, in astrophotography, you take a whole bunch of pictures during a whole night, and then you have to process the photos to kind of align them and get sort of higher resolution from what you get normally. And I actually wrote a PyTorch script to do this. Okay, you can just you can buy packaged software to do that, but I found that boring, so I actually wrote my own PyTorch script for that. I mean, it's using PyTorch and NumPy and various other things, but then the main kind of hobby, if you want, that I have is that I build electronic music instruments. In particular, I build electronic wind instruments. So I have those little things, which actually I talked about this in a talk that you can find on YouTube now, which are like, kind of like saxophone recorder like things that have a microcontroller and they talk to a synthesizer. And I put all kinds of sensors in them and all that stuff. And I've always been fascinated by the use of technology, computer technology in particular for music. The first computer I bought, which was in 1977, which was a single board computer, the first thing I did with it was, play music with it. So.
Very cool. Well, if you are actually tuned in to next year's PyTorch Dev Day, then we can get Jan to play some of his music instruments. Well, finally, Jan, I really wanted to thank you for being here today, and I really appreciate you taking the time. I know how busy your schedule is. And do you have any other thoughts you want to share or talk to the audience about?
Well, I want to thank you for being here also and having this wonderful discussion. I think the future of AI is likely to be very exciting. I think we're going to go through another revolution in AI, perhaps brought about by things like self-supervised learning. I'm really looking forward to it. I hope it happens before my brain turns into mush.
Let's hope for that together. So I hope you had a great time with this session, but I also wanted to ask you to go check out the really exciting talks we've had earlier today, especially on PyTorch Live, the new PyTorch release, the PyTorch ecosystem updates, and the talk that Lynn gave on our vision. So please go check that out. I'm really excited about this.
I'm not. Hold on a sec.
5 years is a long time in the AI community.
What are other people saying for this question?
Basically, I see PyTorch potentially everywhere. Machine learning has the ability to change everyone's lives in a positive way, and I think that PyTorch can play a key role in this.
I hope in 5 years we would have solutions which will really take into account responsible AI and green AI.
We are taking a huge ambitious vision of providing very highly flexible APIs for our researchers, but also provide highly scalable and performance across all devices, all hardware, making it very, very ubiquitous for all of our both researchers, developers, and our community.
So I've always been interested in what's possible at the frontier of technology.
I'm very passionate about democratizing AI and ML. I'm very passionate about creating things that other people can use.
It's far-reaching in terms of how it impacts our lives when we drive our cars, when we go to the doctor, when we live our lives every day. And I think this is just the beginning of the improvement that AI can bring to the world.
I think AI is like changing the world quite a bit, and it's really important to make sure that that impact is positive.
I also feel really strongly about privacy. I feel that users have a right to know what happens to their data, and I feel like research in privacy-preserving ML techniques is the way forward for the entire industry.
If you're going to be interested in machine learning, I feel that working on PyTorch is the best place to be, because it's really widely used and widely respected within the community. And so work that you can do to improve PyTorch has a huge impact on the evolution of machine learning as a whole.